Hello. Hello. Good evening. Good afternoon.
Good afternoon.
Good afternoon, Allison. Oh,
Good
hello. Good afternoon, Key. Double good afternoon to Key. Little video action. That's awesome. Even for 1 minute. I appreciate it. Good afternoon, Bree. Good. Who did I miss? Wait. Okay. Well, there goes Key. It was good to see you, Key, honestly. And you can submit that. You could, even if it was a mistake, you could submit. Okay.
Good
Okay.
afternoon.
Oh, good afternoon. Was that Valentina? Good afternoon.
Yeah.
Okay, great. Good afternoon. Thank you. And good afternoon, Samantha. Good afternoon, Key. I said good afternoon, Alexis. Good afternoon, James. Good afternoon, Juliana. Good afternoon, Dante. Good afternoon, Bree. Okay. Wait. Oh, um, Bradley. Good afternoon, and good afternoon. I missed somebody. Okay. I am. All right, let's just get going. I still don't have your exams. Something as rough is happening on my, and I'm sure you're even more tired than I am, and tired of hearing that. You will get them, I promise, and we'll talk about it. And you'll get them you'll get them like over the next couple of days somehow. And then we'll talk about Monday how we're going to wrap this all up. It'll be less to wrap up than you had to deal with on the midterm. But I'm just going to get, and there's no more homework. It's just the one that was due today, which if you've already turned in, you've already gotten at least I think you probably got at least 50 of the points out of 65 if you've already turned it in, and you'll probably get all the remaining shortly, but you could still turn it in, blah, blah, blah. I'm going to go straight. All right. So I'll answer any questions, obviously, but I'm a little off even my normal kilter. So we're going to get straight to it. When I say it, what I mean is the homework sheet, the fields sheet that was due today specifically. And again, we're going to do it, but you still can do it. But I specifically mean I want to, oh, okay, yes. Oh, did I mess up? Wait a minute. Hold on. I see something in the chat. I'm sure I missed it. Wait. Yes, I'm sorry. You're right. Let me fix it right now. And someone's coming. Thank you, direct chat person. And there's only one direct chat person. So if you're in the direct chat, I'm talking. Thank you. I'll fix that right now. Hang on 1 second. See, I'm totally out of, but thank you. And you should submit that for points. Hang on 1 second. What did I do? And you can keep those kind of like, I'm not trying to stop any of you. Good afternoon. Good afternoon. I am not trying to stop any of your questions, wherever in the material they are. Oh, yes, I see what you mean. I did read. Okay, hold on. I'm just fixing. Tonight's game turn is meant to be game turn 12. This is class 12 out of 15. I accidentally wrote it as 11, as somebody just pointed out. Okay, thank you. It is now fixed, I believe. You could check, or maybe you should check. All right, but what we're going to go over. More people are here. Okay. What we're going to go over or talk about is this business of how to add the vector field contributions from two distinct point sources in order to get one field result. And so we're using the top equation, really. Well, yes, we are totally using the top equation on the board here. I guess I'll add the top equation to be as clear as I can. This is another one of these subtleties that certainly used to elude me. Maybe it wouldn't elude you, but this top equation tells us how to compute the electrostatic field created by a point source or more than one point sources. But the whole idea of this top equation is that it assumes that the charge that's creating forces waiting to happen, that the charges are coming in or appearing in these discrete, infinitesimally sized packets that we call points. just like the gravity equation is telling you what one point of mass does to another point of mass. Now, what as opposed to shapes of charges, this equation does not directly tell you what a wire filled with charge would do, what a line of charge would do, or what a plate of charge would do, or what a sphere, a ball of charged material would do. We have to get to that next. Just like, strictly speaking, the gravity equation doesn't, on its own, by itself, it doesn't tell you actually what the sun does to the earth. It tells you what a point at the center of the sun does to a point at the center of the earth. Okay, just to make that clear. So we're going to do this right now. We're going to solve this one problem that just shows how much computation and what type of thinking goes into calculating a field when you have more than one point. All we're going to do in this problem, or you already did, many of you, and thank you for those of you who already turned it in, all we're looking at here is the field due to 2 points. So part of the actual thing this problem is trying to show is, yes, how we add up the contributions from multiple points to make a full field. Again, this is like in answer to a question or a number of questions people asked in the chat yesterday. Really good questions. But the problem is a little bit thick, as you're going to see, or the solution's a little bit thick, hopefully not too thick, but just thick enough to warrant, like, to become a final exam type problem. It usually does. It's just thick enough to be thick. It's just thick enough to get us involved. And it's meant to show, look how thick this is when we're just doing 2 points. So there's got to be some other ways that we think about fields that allow us to think about anything more complicated at all, like a wire from the lab, or a Van de Graaff generator, or a ball, or a plate. Okay, so again, I'm just trying to emphasize that the equation we have so far assumes 1 point at a time and what impact it's having on the universe. So this equation, this top equation, assumes a point charge, or I could say better, it assumes a point source. It assumes that the source of electric field is a point. Okay, the next 2 equations underneath it is where we're building from here. We have, that's what I want to get to by the end of today's class. The middle equation, just note, the middle equation has some kind of integral in it. I'll get into that in the middle of class, but hopefully if you're getting some pattern of this class or from your math classes, if you recall, an integral is a continuous sum. The integral is the operation that we do when we want to add together the effects of a bunch of smaller pieces, right? Like literally, that's when we use integrals, when we want to add up a bunch of pieces that are so infinitesimally small that there's no separation between each one of them. In other words, a bunch of pieces that are so small and so close together that we can't even count them, right? In other words, not a discrete sum, not a countable sum, but a continuous sum is the next leap we have to make when we want to calculate the field from more realistic configurations of charge. Okay. All right. So I'm just going to get going now again. So there's nothing in the chat. Okay. Good afternoon to person in the chat. I'm going to switch to, so I'm going to change it. So what we're talking about here is, bear with me for a second. Okay. And again, now I'm being, I'm not going to explicitly point out every step of the method as I go. I think I am doing all the steps, but it's up to you to see the steps in what I'm doing at this point. Okay, so first of all, I am doing a diagram. Here's my diagram. This is the plus X direction. This is the plus Y direction. This is the negative X direction. This is the negative Y direction. So this is a coordinate plane, right? And okay. The numbers are a little bit inconvenient, but I'm looking, and again, you should really be looking at your homework 6 sheet on the side while you do. That's what I'm doing. But I'm just keeping this on the screen. All right. So we have at the position 5, 4. At the position +5, +4, we're given in this problem that we have a charge number 1, source charge number 2, and its magnitude of charge is +5 coulombs of charge. I'm just copying from the problem here. That's given, right? Then we've got this, but stop me if I'm wrong. Then we've got this other charge Q2. Did I just put that in the wrong? No, okay. This other charge Q2 is at 10,3. So like here. This diagram is not strictly drawn to scale. The more to scale you draw these things, the better. All right, and this is Q2 is a negative, is like -2 coulombs. Again, so what we got here at the location 5, 4, we've got a humongous number of protons jammed together in a tiny, tiny volume. And at the other location at 10,3, we've got a humongous number of electrons jammed together in a tiny spot, right? And this right here, the origin, you could call this P. Many websites and textbooks will call it the field point. I call it the location of interest, whatever you want to call it. It's the place, whatever you want to call it. It's the place in which we're interested. It's not a special place. Honestly, this is why I don't call it the field point, even though a lot of people do, because I don't want you to think that that point P, there's nothing special about it. There's nothing happening there that isn't happening everywhere else in space. It's just an arbitrary location in space that we're choosing to look at to measure what the field is there. Like if this were literally in the lab, we would put a Gauss meter or something right at that spot and take a measurement. And then we'd probably go around the room and take measurements at a bunch of other places too. And we're trying to, those spots, we're trying to piece together the pattern of what the field lines or the field vectors look like everywhere. So again, just to be clear, this point P, or the field point, the location of interest, is just that. It's the location in which we happen to be focusing our attention, and for which our goal, and this is always true, our goal, like the point of the question, but it's always a goal in electrostatic, always the goal in electrostatics, it is sorry. Oh, and I'm gonna look at the chat, and I see something's in the chat. Give me a second. Let me just write this here. We're always a goal in electrostatics. Determine okay. Well, I'll just read my usual dilemma with it. So what I just wrote was determined E as a function of R. It's always R. Yeah, I'm going to say this and then look in the chat. It looked like there was something interesting in the chat. In general, and you're going to see as we go on, in general in physics, we tend to, we start with examples with little numbers. So we get used to what we're doing with the numbers and what the numbers mean. But then we usually end up getting rid of the numbers as we proceed in physics because we're trying to answer more general questions about general relationships. So ultimately, the whole goal of electrostatics always is if you have a bunch of charge over here, what is the electrostatic field as a function of R displacement over there? If you have charge over here, what's the field over there is ultimately always our question. How does the field function depend on displacement from the actual charges? And then if we have specific numbers like we do here, then we plug in the numbers and we find out specifically what the electric field is at whatever numbers we plugged in, at whatever specific point of interest we're caring about, which we often call P. Let me look at the chat. Oh, there's a lot in the chat, actually. Or, well, wait a minute. Okay, yeah, I'm looking at the chat. Wait a minute. Oh, did I get the numbers wrong? I'm sorry. Wait a minute. No, maybe I did screw something up. Hold on. We thought they had the same y-axis. Maybe I.
Numbers look good.
Oh,
Numbers look fine.
oh wait. Oh, you're saying wait. You're saying
No, your numbers are okay.
Oh, thank you. Okay. Oh, I see what someone's saying in the chat. Oh, I see. Okay. At least one per. Okay. Thank you, Christopher. Okay. So my numbers they are what I mean them to be, but I see why there's some confusion in the chat. Yeah, I'm sorry. Just a quick clarification. On the actual sheet, it looks like because I had to like white out something and I whited it out badly. So it looks like I wrote in the fraction 4/3, or it could look to you like I wrote in the fraction 4/3 and I meant that to be the y coordinate for both. There's at least one person in the chat who that's totally understandable. I see what the person in the chat is saying. It's not actually what I meant. That's my bad. And in terms of your homework, and one person's putting in the chat, that's got to mean he or she is not alone. I mean, so who? Oh, there you go. Thank you, Keith. Thank you for. Okay, my bad. I apologize. That's like a typographic confusion. I'll say this right now, just to be clear. I'm going to go on with the numbers I meant, and you can correct. But hello. Okay. Hello. No. Oh, wait. That's 3 people. Oh my God. I'm messing with everybody. I'm so sorry. Wait, is it? Okay. Wait, but don't say, oh no. I mean, you could say whatever you want, but let me just say, like, literally, not only on the homework itself, like, you don't even have, just on your homework, just add a note that that's what you thought, and it's totally fine. We're looking at what you do with these numbers, not anything special at the actual number. So on your homework, don't even worry about it. And let me reassure you too, let's say something like that happens on the final. If it's a final, at worst, if I think you've misunderstood the question or misread, so maybe I would take off 1 point at the beginning if I think if I really, and this is after I look at it, this is also why it takes me so long to grade exams. Look, believe me, if a bunch of people in the room all have the same misunderstanding, like right now, at least 3 people do, I know that means it's me, not you. I mean, if 3 people misunderstand, I mean, at least it means I left something ambiguous. Okay, so if it happened on the exam like this, and like more than one person thought I meant to blah, blah, blah in good faith, I wouldn't even take off points at all. I promise you. If you're the only one in the world who thought that, and I, in my heart, think, I don't really see how you thought that, like, that's not, then maybe I would take off a point or 2 for like miscopying the number. But then everything from then on is all just based on that. So I do apologize, but don't get stressed about, really, we have enough to be stressed. Like, that is not, don't be stressed about it, please. But I am going to now go on with the numbers that I think they are. Also, let me quick aside too. In terms of the final exam or exams in life, like, I'm assuming that and I do appreciate your honesty. Let me know and I'll fix it for the next, I'll be aware of it for the next semester if I don't fire myself first. But also, here's the thing. I'm assuming that people in the chat just literally thought that, like, they didn't think about thinking about it. They're just like, okay, that's 4/3, blah, 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 right? And that's why at least one person's going, oh no, because it's like didn't even occur, right? But if you're in an exam and you literally have a choice, in life, in all of science, even in really normal conventional exams where you're like under test conditions on it, if you ever have a choice, if you literally are like, wait, does he mean 4/3 or does he mean like 4 and 3 or whatever? Always, if you have 2 choices of how to interpret something, always interpret it the simpler way, the way that will make life easier for you. That is a major science truism and a tip. And I'm not even saying that means you're always going to be right. I mean, some teachers are out to get you or whatever. But if you're in doubt and it's a coin flip, always pick the simpler interpretation, because you will then be able to do more with it. Like, it's like a poker position to take, really. And I'm going to say one last thing about that, as long as we're on this, and I'll go back. This always happens. But if you're in an exam in science, any kind, or a research, right? And you get to the point into the middle of something and you're like, I literally don't know whether to do sine or cosine right now. Like, it could be sine or it could be cosine. It seems like it's a 50-50 chance. I have no idea which is right or which is wrong. Again, even there, what you should always, or that's just an example, obviously, but whenever you have a choice between 2 things to do, always don't choose the thing you think is right, because obviously you don't know which is right, because that's why you have a choice. Don't choose the thing you think is necessarily right. Choose the thing that will allow you to produce more work therein. Like always make the choice that allows you to make more choices. Always take the step that allows you to take more steps. That is a secret. I mean, it's not a secret, but think about it on your own time. But that will get you out of a lot of jams in science research and a lot of science. And I wish I had understood that 30 years earlier. But when you don't know what's right, do the thing that allows you to do more things. Just keep the beat going. Anyway, all right, which I fail to do all the time. So here we go. Back to the problem. Okay, so what do we have to do? So first of all, I said yesterday, are we on? Yeah, I said yesterday, we got to draw a preliminary, we got to complete this preliminary diagram. Here's what I mean by that. We've got the positive charge at 5, 4. It is pushing, right? It's pushing. I'm just drawing a dotted line for reference for myself. It's pushing onto point P. It's pushing, like this dotted line that I'm drawing, in effect, is R1, right? It's the displacement vector from source number 1 to the field point. So there's going to be a field vector starting at P that goes in that same direction. It goes in the same direction because the source is positive. There's going to be some kind of field vector going like that due to Q1, right? I don't know. I'm drawing it roughly. I don't quite exactly know how long it is yet. That's what we're going to figure out. But I do know it's going to go in that direction. Then I also know from Q2, there's a field vector. Now here's R2. And let's be literal, like R1 points to the point P from Q1, and R2 also points to the point P for, like, maybe I should do a different color, right? Those are the R vectors, the display, and I know how long they are, or I mean, I can figure out how long they are, but they're going to produce E field vectors, and the E field vector to Q2 is going to be also along that line, but because Q2 is negative, it's going to point toward Q2. So it's going to be something like this. Now, I'm drawing a rough sketch here. This is to give me a sense of direction and a sense of comparative magnitude. I don't know the literal magnitudes of those E field vectors yet. I'm going to call them E1 and E2. What I know is that my goal is going to be to add up those two vectors and I'm going to add up those two vector contributions and get one net vector, one E field final result. But I do know that they're going to point in those directions, right? And I notice in my diagram, I'm like guesstimating that the arrow pointing to Q2 is shorter than Q1. And it probably is even more shorter than I made it. Like I didn't make it significantly shorter, but I made it shorter. Now, please note that I'm not saying R2 is shorter than R1. R2 is definitively longer than R1. But that's part of why I expect that E2 will be shorter than E1, right? I'm saying Q2 is farther away from the field point than Q1 is. It's farther away. And the whole idea of this whole thing is that fields obey an inverse R squared law. So all things being equal, Q2 would pull less on P than Q1 would push. But then on top of that, all things are not equal because also the amount of charge matters. And Q1 is a bigger charge magnitude than Q2 is. So the two factors happen to be in correspondence. Like Q2 is both smaller in magnitude and farther away. So I'm pretty confident that it's going to make a smaller field contribution to the field than the contribution made by Q1, right? So that's my sketch of what's going on. So now I'm saying that ultimately, it's a sketch. I'm ultimately even saying Now this is also not going to be. Yeah. Something like, now I really should be more careful if I had graph paper or something like this. Something like. Yeah, like just to be, so this is again a sketch of what's going on. I'm not, what's going on is we're adding up, like I'm now putting the two vectors tip to tail. You notice this is what's going on in space. We've got a push on a certain point and we've got a pull on that point, both acting on that point. So that's the diagram of what's happening in space. To think about how those two vectors are interacting, they're being added together, right? I mean, field produces force, force obeys F net equals MA. That is, we believe that forces superpose. The sum of the force, the net force on an object equals the sum of the arithmetic, the addition, the sum of all of the forces, each acting as though each one acting independently of every other force to which it's being added. So these vectors are being added together to make one full vector. When you add vectors, you put them tip to tail. So if I'm even remotely to scale, which I'm a little bit worried that I'm not at all, but if I'm even roughly to scale, this diagram is showing me that I should expect at the end of the day, my final answer, hopefully, and you could stop me right now if you, oh, can I go back for a second? I'm sorry. Oh, wait, okay, wait, there's a lot going on in the chat. I'll finish the sentence and look in the chat. I do love how much you guys do participate, seriously. But if my diagram is right, and it's possible it's not, it's possible that people are telling me in the chat that it's not. But if my two arrows are correct, roughly, and then I put them tip to tail, then that would, then the net result of the whole thing should be an arrow that points from the original tail of the first, or the tail of the original vector, all the way to the tip of the second vector. Like that's how vector addition works, right? The resultant vector is the third side of the triangle formed by the other two vectors. And the whole idea, and I will look at the chat, you know, that's all very abstract. And we spend a lot of time on in physics 203, and it's like one of those many things in physics that you either get or you don't until you do, and then you do. But it's all based on how we believe walking works. It's why we, at least at John Jay, start this whole thing with that sort of silly, but sort of not lab number 3 on the graph paper, where you're like trying to get off Survivor Island or whatever, like just to say to everybody, this, remember, this whole vector idea stems from us believing that all vectors act ultimately like displacement vectors, and displacement vectors act the way you do when you walk, like when you walk city blocks, right? I mean, if you walk 10 blocks to the south and then you walk 5 blocks to the east, where you end up is the vector sum of those two subwalks that you just did. And you can picture where you end up by literally taking your first walk and representing with an arrow, and then starting your second walk with a tail placed at the tip of your first walk. Like that did not help at all. But I'm just saying this all assumes that all vector quantities add the same way displacement vector quantities would, which is tip to tail. Now let me look in the chat. Something's definitely happening in the chat. Hold on. Isn't that arrow supposed to point outward for positive Q? Yes, did I not do that? The positive Q. Wait, so I think, oh, can I go back for a second too? Wait, do you want to go back? I don't know if this is, so someone's asked, oh, Chris has asked me to go back. Is this the page you want me to?
Okay, you already went back.
Oh, okay. All right, so then there's a question in the private chat. Isn't the arrow supposed to point outward for positive Q. And I think that that is what I'm doing, but okay, but this is the confusing part maybe. I believe that my arrow from Q1, from the positive Q, like I agree. Let me start by saying, someone wrote, isn't the arrow supposed to point outward for positive Q? So first of all, yes, like that. Oh,
I'm
that,
sorry.
so that,
Is there a possibility that you can use 2 different colors so that we can better see it?
sure.
Like,
Okay.
I know that Q1 goes straight into negative, but I think if we had like better colors, it would somewhat look noticeably different.
Okay, I think I understand. Let me check. So, okay, let me, sure, let me try. I mean, because this is, okay, sure. Tell me if the, let me, okay. Let me start by saying, and this might be clear too when I write yet a third diagram, but let me start by saying from Q1, what I definitely agree, what I think the direct, oh, good afternoon, thank you. What I think the direct chat person is, oh, sorry. And let me start by saying, the direct chat person's question is very good. He or she is asking, isn't the arrow supposed to point outward for a positive charge? Well, the answer is definitely yes. So like, he or she is right that arrows from positives should point outward. Now, and I think though that that's what I'm doing. I think we're just having a little confusion about tips and tails or colors or something. So let me start by saying the R1, the displaced R, right? R is the displacement vector on which our field vector is always based. And then this is the thing I was talking a lot about yesterday that is, it's a lot in a way. I am trying to have you all picture that the field equation, it's truly a vector equation. It's not just a vector equation in that it spits out something with magnitude and direction. Like it does do that. It does spit out an answer with magnitude and direction, but it's more than that. It's a function whose input is a vector and whose output is a vector. It's ultimately really helpful to think of the field equation, the one that we're dealing with here. I'll write it again. It's a little bit hard at first and maybe seems like over much at first, but it's ultimately really helpful to think of this equation that I'm writing down right now. If you think of it as an operation that you're performing on a given vector, what you're doing is you're taking a given vector that already exists, and then you're stretching it or shrinking it by a certain amount, and then you're possibly or possibly not flipping it. Like, and when you shrink, let me say that one more time. You're taking an original vector. The original vector that you're taking is the R hat vector, which is kind of why we need to get used to that new notation. R hat is a vector. It is the unit vector for the displacement vector that points from source to location. Right. And again, that's a lot. You have to sort of go over this in your mind. I mean, but that is what it is. The R hat vector is the unit vector for the displacement vector R. Like again, I'm saying R is this. Right. So I'm saying the way we construct the field vectors, first, we picture the displacement vector. First, we picture the distance and direction from the source. So I'm trying to get this back to the direct chat person's question, I promise, and to Chris's colors. But what we're saying we do here, when we construct the field vector or we determine, find, compute, whatever, when we find the field vector, the way we do it is we start with the vector that we already have as our input. The vector that we start with is the displacement from source to location. That's called R vector. So in this case, going back to the diagram, back to the problem, if I look at Q1, which is my source, I can draw an arrow. Okay, so I'll draw it in a color. Like, oops, sorry, not that color. Sorry. I can draw an arrow from Q1 to the location that we're interested in, the origin, what we're calling P, right? I draw this blue arrow. It is called R1 vector. It is not my answer. It's not my answer. It's the displacement from the source to the location, and it's that displacement that sort of everything is going to be based on. Like this is like the input or the the independent variable for the function. So then what do? Then I say to what we're going to do to create the E field vector that results from that, what we're going to do, first of all, and this part I'm not sure I'm going to draw. First of all, in our minds, we picture the R hat vector. Like from this long vector that points in a certain way, then maybe I can in a different color. This might get clunky, but I might erase it. But we say to ourselves, there's a little vector called R1 hat. What is that? That is deliberately, like it's a vector that we design in our mind that literally explicitly points in the same direction as R1, but has a length of 1. Now, let me say again, for people that are tuning in and out or whatever, the little subscript ones that I'm using right now are all because I'm just dealing with point source Q1. Okay, don't let those throw you. Like, I'll do the exact same thing in 20 minutes on source subscript 2. So all those, but whenever you make a unit vector, I don't care whether it's called R sub 1 or R sub 2 or R sub 3. When you make a unit vector, when you put the hat over it, then what you're doing is you're designing a little vector that has the exact same direction as your original vector, but it deliberately has a length of just 1. What we're doing in principle is we're taking that vector. In order to find the field vector, we're taking that vector. And first, we're going to multiply it by a bunch of numbers multiplied together by like the electrostatic constant, which is 8.99 times 10 to the 9th, times the amount of charge, which in this case is positive 5 coulombs, right? And those are all in certain units, like newtons, meters squared, coulombs squared. Then we're going to divide by the square of the distance r. Notice we divide by a number. We divide by the square of just r itself, not the vector, the magnitude of the vector, and not the magnitude of the unit vector, because that would just be 1. But we're going to divide by the length, the actual distance from Q1 to the point source, right? And we're going to do all of this, but I'm saying like the thought process, or what we're supposed to be imagining is happening, is that first, we took the displacement vector, which is blue and pointing down there to P. Then from it, we constructed a unit vector, which is red and has a length of only 1. Then we take that unit vector, we multiply it by all these numbers, right? We multiply all these numbers. We change its units from meters to newtons. So we get a new big number that's measured in newtons now, right? And then we look at whether our new number is positive or negative. And in this case, it would be positive because the original source is positive. And if the new thing is positive, then we say, okay, that R hat vector that we just scaled up or scaled down by all these crazy numbers that we just multiplied, that's going to give us our field vector. And since it's positive, back to the direct chat person's question, since it's positive, we're going to make an arrow now that's bigger than R hat, or that's a different number than R hat because we just multiplied 1 by a whole bunch of crap. But we're going to keep it in the exact same direction because we got a positive answer. So we'll be in the same direction as R hat. And this final vector that we're getting, this final vector, and notice please again, to get this final vector, we divided by R squared. We didn't divide by R squared times R or R cubed or anything. Like the R hat was not a multiplier in any of that arithmetic. The R hat deliberately as a magnitude of 1. Like that's why we use it. It's there to tell us the direction, but it doesn't mess up all that multiplication. The multiplication just takes into account magnitude, lowercase r squared. So finally to the direct chat person's question, and this will either help or confuse people more. At the end of the day, we get a field vector. I'll do a totally different color. We get a field vector. And the field vector represents what is happening at the point P, at the location. So the field vector that I'm going to draw now, back to direct chat person's question about whether it should be pushing or pulling, what I believe is from all of the math that we're going to do, I'm just drawing a sketch predicting all the math we're going to do, I believe we're going to get a vector that's telling us what's happening at P. So the tail of my vector will start at P, and an arrow will come out at P, and that direction of that arrow will represent what I think would happen to a test charge of 1 positive Coulomb that could be located at point P. In other words, I'm now going to draw an arrow that's like somewhat like this. Again, this is not to scale. It's a prediction. It's a sketch. We're going to get the exact numbers in a minute. But this green arrow that I'm now drawing here. In fact, wait, let me make it even, I'll make it even more, let me make it even more clear that it's not the same arrow as the blue one. Like, it is its own length. It does not have the length of that red arrow, which is the unit vector R. There's no reason to expect that it would have the same length as R1, because R1 is displacement. It's how far away the two charges are. This thing is force per charge. This is newtons per Coulomb. This is this green arrow is the answer from Q1 that we're looking for that got built from the red arrow R hat, which got built from the blue arrow R1. I'm going to pause in a second, but I'm saying, and again, it's not really to scale. Honestly, when you work out all those numbers, depending on what they are, maybe the green arrow is even smaller than the blue arrow. I don't know that offhand. I do believe that this green arrow is going to be bigger than the green arrow that I get from Q2, but I don't literally offhand know how big it is. What I know is there's no reason to assume it's the same size as the two that it was built from. But I do know this, and I will shut up now. I'm going to pause, I'm going to check the chat, but I believe this green arrow, I think what maybe got someone thinking in the direct chat is this green arrow, it is a push. I'm saying this is a push. This is, but the tail of it starts at P because it's showing me that if I had 1 positive Coulomb of charge, of test charge sitting at P, if I had a little proton sitting at P, it would be shoved along the direction of this green arrow. It would be pushed away from Q1. It wouldn't be pulled, it would be pushed. So this green arrow is pointing away from Q1. But this green arrow starts at P because it's telling me what's happening at P. I'm going to pause. Oh my God.
I have a question.
Wait, sorry, hold on. Wait, you are going to go, but wait 1 second. Sorry. Hold on. There's like kind of a vague emergency chat here. Wait 1 second. Not emergency. Okay. Oh, 1 second. Okay. And 1 second. Okay. And direct chat person who said you got it now. Thank you for saying that. Cool. Okay. Thank you. Okay. I appreciate it. Now, Chris, go. Sorry.
Okay. Earlier, like in the week when you were explaining source and test, test charge, right? Mm-hmm. I could be wrong. You said something like the force exerted from the source to the test, but I think like if it was positive, it would be exerted back to the source. Is it somewhere?
Wait, well, you're correct. Wait a minute. Everything you're saying so far is correct with one modification. Yeah, whatever the source does to the test, absolutely. The test, if we're talking about forces, whatever the source does to the test, yes, the test has to do back to the source. That's true, whether they're positive or negative. That so far is definitely true. Yes. Okay, so keep going.
Oh, I thought like if there was a different charge on the source, like if the charge was positive instead of negative, it would. I don't remember what you said. It was something along that line that like if it was positive, it would come back to the. I don't remember because that's how I'm kind of trying to interpret it. Like right now, I thought it would actually go back to Q1, but
what we might see better when I do the other one will, like when I draw other picture, maybe I'll try to do that right now. The green arrow for Q2 will point back to Q2. Okay, let me back up for a second. And again, everybody, this, I feel like this is worth it. I mean, if you guys, well, I hope people aren't, I assume that this is what we're here to talk about. So I hope other people feel free to also get involved or whatever. I am saying that the field, here, let me back up for a second. The force is something I do to you, right? But field, like in other words, force is something that one object does to another object. You got to have two charges involved for there to be a force. But this whole field notion, which is new. Oh, cool. This whole field notion, which is new, is new. The field notion is that it's what one source, what one object does to a point in space. But what is it? What are we calculating? Like what we're calculating, it's kind of a conditional thing or a hypothetical thing or a prediction thing, which is why we always call that second charge, that receiving charge, a test charge, because by the time we now get to this field discussion, the point is that there is no second charge really anymore. But what, I mean, there isn't. Like the field, the idea is that the field vector is there in space, whether or not there is any charge, any receiving test charge there in space. What the field vector is saying or containing, or what the field vector means is this is what would happen. This is our prediction. This is all the math already being done. This is what will happen. Like this is how hard and in what direction something will be pushed or pulled if there were a positive 1 coulomb of charge at this location that we're testing. That this might be the thing that Chris is remembering. I'm not sure. Oh, wait, and I'm going to see the direct chat in 1 second. But the key thing, and I promise, and one of the reasons I'm like really dwelling on this with you guys and taking these questions, it's not just to be polite. Like I swear, you're asking the questions that really, really confused and got me all messed up myself. But I think you're smart enough to ask these questions a lot earlier than I ever was. Like these are very legitimately confusing aspects. You are not alone. And I only understand them now because I went through the confusion and eventually got unconfused. And I don't think I did it as efficiently as you guys. So here's what I'm saying. The thing that I never got that might be escaping you right now, is that the field assumes that the test that would be there, that we're predicting for, it assumes that that thing that we are predicting for would be positive, no matter what. Like the source can be positive or negative, and that's what we're on purpose doing in this problem here. We're going to draw the two different vectors for the two different sources and see how like a positive source sort of pushes and a negative source pulls. But the reason we say that, the reason the source pushes, and the reason a positive source pushes and a negative source pulls is because what we're predicting, what we're saying is that's what would happen to a second object at some, wait, we're saying a positive source pushes on a point in space or a negative source pulls on a point in space. It's because what we're imagining, what we're predicting is if there were a positive at that point in space, what would happen to it? Well, that's not an example. That's a rule. Like the test that we're imagining by convention is always positive. The test is always positive in our imagination of constructing a field vector. So regardless of whether the source is positive or negative. So we are imagining that if you had this Q1 positive source here, and we're asking what effect does it have on the point P down there? Well, what we're ultimately saying is it's going to throw a green vector right on point P. It's going to throw a green vector on point P, meaning the tail of the green vector on point P. And it's going to be this long green vector pointing away from Q1 because we're saying if there was a proton at point P, it would be shoved away from Q1. Whereas in a moment, I know I'm yelling, I'm not angry, I'm not excited, I'm actually just waking up probably. But in a moment when I draw the green vector for Q2, again, I'm going to put the tail of it at P because we're trying to ask what the heck is going on at point P. But that green vector will be pointing up toward Q2 because if I had a little proton sitting at the origin of this coordinate system, it would be yanked toward Q2. But I think and I'm going to look at the chat in a second. I don't know if that, and I'm going to keep doing the color thing. I don't know. I think the thing that Chris is remembering from the other day is where I maybe is that I'm making a big point saying like test is always positive, whereas the source could be positive or negative, or maybe that's not what he's remembering, but there's also something in the chat. I do honestly think that part of why the original person asked this original question is I think it may be a little confusing to people that I've shifted the tails of my vectors from Q1 to P, but I'm doing that on purpose because they are two different vectors. The original vector R is a vector that's meant to point from the original source to the location. It's saying how far away are these two things? And then the final vector that we're computing is the vector that we find to be existing at that location. Okay, I'm gonna look at the, there's a lot of things in the chat, good. And of course, Chris can also like, I'm gonna try to get other people too, but of course I wanna ultimately know whether like Chris is satisfied or not, or whatever, and that applies to everybody. All right, hold on.
No, that helped. I think I was mixing up forces with the fields.
Oh, okay.
I was, yeah.
Okay, cool. And that, okay, good. No, and I appreciate your honesty. And again, with everybody, it makes me so, yeah, I love the questions. I love the follow-up and like, and and confusing forces with fields is a very, very natural thing to do. Okay, but cool. So I'm looking at, so there's things in the direct chat. So applying R hat would change the values that we would. Okay, here's one question in the chat that there's a lot of things in the chat. I'm sorry. Okay, so I may be a little bit out of real time here. This is about the term for, there's like a intellectual latency in my like life. Okay, anyway, because there's a thing here in the chat that says, something in the chat says, so applying R hat would change the values that we would plug into the equation, question mark. The difference between the X values is not what we use, question mark. No. Now, again, that's a really good question and a really honest question. And you could sort of tell, or I could sort of tell by the way the person's writing it, like they're kind of saying, wait, I thought I had this a minute ago. Now with everything you're saying, Yaverbaum, I feel like maybe I don't have this anymore. I'm reading between the lines, but let me say, no, I'll read that question again. But actually, I think the person who wrote it did have it before and was fine, and I don't want to throw him or her off. Let me say this. R hat is super important. It is important and difficult to understand R hat. It was a big stumbling block for me. I don't want to make it harder for anybody than it is, but I want you guys to get it. It is important. It matters in all this, and it particularly matters when we get to magnetism. However, the one thing that R hat does not do, the whole sort of purpose of R hat, is it doesn't change the values. No, it doesn't. If you thought, you direct chat person, if you thought before that you were doing something with the X's and the Y's to get our answers, which I will, I promise I'll do if it's the last thing I do today. If you thought that the way to get the actual numerical answers is to just like churn through the X's and Y's carefully, and if you think that that R hat didn't change your numerical answers, I believe you are correct. If you do it right, R hat is not supposed to, the point of R hat is it doesn't throw off your numerical values. It does not, but it signifies direction, particularly when it's taken along with a positive sign or a negative sign. And B, to be honest, I'm making a big deal of it. It's like one of these things that I do. I'm making a big deal of R hat now when it's doing just a little bit enough that we can hopefully see it. I'm not saying that it's doing a huge thing. Like, to be super honest, we could get away with all of this. We could get these answers that I'm going to get soon. We could get the answers without even introducing the R hat, and kind of like what Hema might have done really fast with gravity last semester. We could get away with getting the numerical answers without R hat. We might even be able to sort of intuitively talk to ourselves about what's happening in the direction without R hat. But I'm sticking in the R hat right now. I mean, I'm not sticking it in, it's there, but I'm trying to get you all to understand the R hat thing now. While it's not making a huge difference, because it's easier to understand now when it's not making a huge difference, it does make a huge difference in magnetism. Okay, so honestly, I want you to get it, but don't get overstressed by it. It's there to signify direction. And it's the direction of the displacement from the source to the point. Oh, one last quick thing again, sort of back to part of Chris's question. Every time we're talking about fields, no, let me go back. When we're talking about forces, R means the displacement from one object to the other object. When we're talking about forces, R means the displacement from the source of the force to the receiver of the force, which we call the test. Now that we're in field land, the whole big new breakthrough is we don't need a second object anymore to be talking about this stuff. We're basically saying we can do a lot of math and predict a lot of information in advance before the second object ever comes along. What we could do is just what we did with the homework yesterday. We could say, why don't we just predict in advance what would happen to any one positive Coulomb of charge that would maybe ever come along to a point in space? And whatever that prediction is, we're calling the field. And here's the big deal. We first saw it as a mathematical trick. And again, obviously many people, including Chris, were very involved in that mathematical trick, right? First, it was just like hey, wouldn't we save ourselves time if we would just predict first what would happen to a one positive Coulomb receiver? Because once we know that, then any receiver that you could possibly pick, we'll quickly know, we'll just multiply and then we'll know what the force is. That's what we did first. And then I'm saying, guess what? That's what the universe does too. Honestly, I'm saying, the universe, space, so the minute you put an object in space, somehow all of the information of that object goes to every point in space and sits there like a little bundle waiting to be multiplied by whatever comes along. I'm not literally saying that the universe sits there with a calculator, and I'm not trying to be crazy, but I'm trying to get you to see that the information bundle that we compute here in this problem that we call the field being the prediction of what will happen at any point in space to any point that could be at that space, any point of charge that could sit at that space. I'm saying that actually happens in the universe. The information is there in space before anything else comes along to experience it. That's why we care about it so much. It's there in space. It's called a field. It's just like sound waves are in space or in the air, even though just when you have a bucket of air, that doesn't mean you have sound, if you know what I mean. Sound is not the same thing as air. It is not a thing, but it's moving through air, and you know it is, and you feel its effect. Field is like that. Field is this bundle of information. Okay, so with the field, R vector doesn't mean the displacement from the source to the receiver. It doesn't mean the displacement from the first object to the second object. It means the displacement from the first object to the point in space that we're investigating. Okay, just dropping that in the end. So that's what R means in this context. It's the displacement from source to location, and on that display, that's like the input to the field function, and the output, the field itself, is totally a big bunch of math that's done to that vector. It's a big bunch of scaling up and scaling down and then possibly rotating of that vector to produce a final new vector that we're trying to solve for. Okay, I'll shut up. I'll go back to the chat. Sorry. Okay. So I don't know if that answered the question about R hat, but so R hat, the R hat won't really change the numbers. It's there to perform some directional work for us. Okay, I'm looking at the chat. Oh, so maybe this is repeating. Oh yeah. Totally. All right, just going to repeat this. Yeah, it is. So someone wrote in the chat, maybe this is repeating what you said. Or I'm more likely it's another perspective on what I said. But it made sense for me when I looked at the units, newtons per coulomb. And she or he is right. The units of field is newtons divided by coulomb, newtons per coulomb. So it's how much force it does per coulomb. So the force would be higher for stuff with more coulombs. That's totally right. Yes. I tried to put it my way. That's another slightly different way, but yes. And if that worked for anybody, good. It's right. Yeah. Force is newtons. Field is newtons per coulomb. And that's also why, if you look in the equations, in the force equations, there's Q1 and Q2, but in the field equation, there's just Q1. It's all the information regarding Q1 waiting to happen. It's how many newtons of force would be exerted on each coulomb that we could imagine being at some location. Therefore, if there was 2 coulombs at that location, the force experienced would be 2 times the field. If there was 3, it'd be 3 times the field, etc. So yeah, I totally agree. That's great. Okay, more. Are we ever asked? Oh, that's a great question. Bradley's question to everybody. Are we ever asked to draw a field where the test charge isn't +1c by default? You know what's perfect about that question? Is that maybe I can answer it in less than a half hour. The answer is no. But it's a great question. You never will be, because you nailed it. Exactly what you, Bradley, wrote in the chat. I'm going to say it again. He wrote, are we ever asked to draw a field where the test charge isn't +1c by default? The field is, by definition, I like the way he put that. It is always, by definition, assuming a test charge of +1c by default. Any field you ever draw, always, and it's not just you students. I mean, any field line diagrams on computers in the world are always showing us how many newtons would happen to each +1 coulomb by default. Now, that doesn't, so what that means, going back to the other direct chat person's rephrasing, is then if you ever do have +2 coulombs experiencing the field, that's perfectly reasonable. Like what we're saying is field, I'm going to erase this in a second because I'm running out of, but if we're saying that field by definition, if we're saying that field by definition is net electrostatic force per charge, then it means, if field by definition is net electrostatic force per charge, then the whole point of that, it means that net electrostatic force acting at any moment is whatever charge is there times the field. So all diagrams in life, I mean, it's a great, Bradley's question is perfect. All diagrams, all these constructions of fields are always assuming +1, but it doesn't mean we're then limiting ourselves. It means we now have, it's exactly like what we did in the homework yesterday. We now have the answer for like the per coulomb force. So well, then you go to reality and say, oh, but guess what? There's 3 coulombs sitting here in the field. Now what do I do? Well, then you say, oh, well, then the force is whatever the value of that field is times 3. Like that's the total point. So the answer to question, to Bradley's question, is no, but that's because the way Bradley put it shows he exactly understands. Okay, would we just use the original with 2 Q values? I think, wait, is that an answer to Bradley? Well, first of all, I love the fact that you guys are replying to each other. I may be reading this wrong. Wait, okay, I'm losing this, and I know I have to get, and again, I'm telling you, I apologize to people if you think we're like going off. I know you want me to get back to the sheet, some of you, and I promise I will, but I really think this discussion is more valuable than anything I can say linearly. So hold on. So I think James was responding to Bradley's question, and yeah, like if you ever have the 2, see, if you know the 2 original Q values, if you know Q1 and Q2, then you're already talking about a force. So yes, you would use those 2 values. I mean, another way to put all this, I suppose, is the field is the idea that we use when we don't yet know the second Q value. And again, it's not just a math thing or a human like, oh, we don't have the information. What we're saying is this is what's going on in space. I'm going to say it one more time, but there's more happening in the chat, but like, well, no, I'll probably say it at the end. But I'm saying, like, we used to say proton pulls electron. We don't say that anymore. We say the minute proton appears, even if before there's an electron, the moment there's a proton, it's already creating something in space. It's creating a tractor beam, metaphorically. It's creating an influence in space ready to go, that then the minute the electron gets there, the thing in space pulls on the electron. And that's what we're trying to compute. But yes, once you know the value of both charges, then you're already at the level, then you're like space. You got both objects there. You've got a force, no problem. I'm going to resend my message. Yes. Oh, okay. Okay. I see the direct chat. Sure. Okay. So then we have in the general chat, we have the repeat of the thing that I read before because it does seem to help people. So that's cool. Thank you. I mean, Evelyn was the person who wrote it before. She put it in she put in the general chat. Thank you. I think we're good with that now. And then Alexis. Oh, sorry. I mean, various people. Okay. 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 Thank you, Bradley, for so all of you have participated in this, and I really appreciate that some of you that have participated are like, I mean, there's some variety in the people that are participating, which I really appreciate, and I appreciate the like, closing the path. Okay. Now I know I have to speed up. Yeah. Let me slightly speed up and try to. But I'm going to say one more. Well, am I? Just please remember, maybe you were warned about this at the beginning of physics. Everybody's always heard that physics is hard, right? And then there's a way we teach it at John Jay that we try to show you, at least at first, that in a way, physics is not hard in the way that you thought it was going to be. And in a way, physics can be a lot easier than people think. And all of that is true. It's much more natural and approachable than sometimes people think. But the thing about physics is really honestly why it's hard is honestly because the way it's hard is not the way you expect it to be. The hardest thing about physics is that whatever way it's hard, it's not the same way as chemistry and biology, right? I mean, I could talk for days about this, but it's not about it's not complex. There aren't a lot of details to manage. There isn't a lot of information that you get or that you have to deal with. So in a way, at the beginning, it seems almost like a joke or a relief or something. It's true. There aren't that many equations or that many facts to memorize, but that's actually in the end what makes it hard is that it's simple. We just have a few building block ideas that we're churning through over and over again and somehow explaining the whole universe with. So you really have to get your mind around these building block ideas. And there's not a lot, in the end of the day. Well, anyway, you get my point. So I'm saying that with sympathy. I'm saying if you're suddenly like, wait, what is going on? I thought I got this, but I don't, but it doesn't seem like it should be bad, but it is, or what? Like, yes, welcome to my world. It's slippery. It is ultimately all very manageable. It is logical. There's nothing, I hope you can at least see that anything you ask me, if you give me enough time, I can break it down to things that you do believe and agree with. I hope you see that. And that's not because of me. That's the nature of physics. But it does take time to do that. You have to let the ideas sit. And that's why like we do tests the way we do, blah, blah, blah. All right. So don't give up. I guess I'm saying don't walk away. I mean, walk away if you need a break, but don't say, forget it. This is over my head. It's not over your head, whoever you are. And all these questions are great. Okay, so I'm going to do the other vector. The other vector, I'll do it sort of quickly. I'll try to do sort of quickly. The other vector, first I start with R2. R2 is the displacement from Q2 to the field point P, right? So I'm drawing, sorry, hello. So I'm going to draw that in blue again. Maybe that's annoying, but I'm drawing it in blue again because that's another R vector, right? This is now the vector R2, vector R2. Its tail is at Q2. Its tip is at the field point, at the origin. It's pointing in. Now again, notice both of those vectors are pointing in. This might have been what started the confusion 20 minutes ago. Because both of those are R vectors. They're both meant to be the displacement from the source to the location of interest. So they're both landing on the location of interest, the origin, right? Then, and that's irregardless. It doesn't matter that Q1 and Q2 are positive or negative or what. The R vector is the R vector. So then from the R vector, I construct the R hat vector, right, which is a vector that points in the same exact direction as R, but has a magnitude of 1. So here's my R hat sub 2 vector, okay? And that's just, I'm part of what I'm doing this also so we just picture what's going on. I'm not saying that you would grind through math on all of these arrows necessarily, but anyway. Then we say, okay, the field contribution that we're trying to look at or picture from Q2, the field contribution, what I'm calling E2. I need green. Where's green? Okay. That field contribution is going to be an arrow that I make in my mind, or we make from the math by taking the R2 hat vector, first, we're going to blow it up or scale it up or whatever by multiplying it by 1 over 4 pi epsilon naught times Q over lowercase r squared, right? Like I'm going to multiply it by a whole bunch of numbers, one of those numbers is the square of the distance of just the magnitude of this original r vector, right? So put it one last way, I guess I'm saying that original r vector is key to this whole thing, because what we really do is we put that r vector down and then we strip it and we use its pure magnitude as a part of the scaling process that's going on, and we use this pure direction as a reference guide to the ultimate direction of what's going on. But it's, we strip it into those two pieces. The magnitude piece is in the denominator squared, and the direction piece is that r hat thing sitting at the end. They're both functioning on their own. So I take this R2 hat vector, I multiply it by all those numbers, and I get some big green vector. And then I say, okay, wait, when I multiplied it by all those numbers, one of those numbers was a negative, because Q2 is negative 2c. So the answer to my whole thing is going to have a negative sign in it. So the whole vector that I get in the end will have some size, but its direction will be the negative of r hat, which means, so now I'm using the direction of r hat as my reference. I say, oh, my final vector, my final E2 vector that is landing on point P, in other words, whose tail will be at point P, is going to be a vector that I ultimately think is smaller than the other one. I'll re-explain that in a second if you want. But I'm getting a vector whose tail is at P and who points directly against the direction of R2, sorry, right? I mean, this is getting to be a lot of details here. But the ultimate E2 vector, right? It's using the direction of R2, but it's flipping it because it has a negative involved. Why does it have a negative involved? Because Q2 is negative 2c. So I know its direction, and then I'm guesstimating, or I'm sketching that its magnitude, whatever it is, it's like all those numbers multiplied together. But if I just roughly look at those numbers, I notice that the r squared in the denominator for this one is much bigger. It's going to be much bigger than the r squared in the other in E1. So the denominator is going to be much bigger. So I think the whole fraction is going to be smaller. Plus Q2 is smaller than Q1. So the numerator of this vector magnitude is smaller and the denominator is bigger. So this final vector that I'm getting is smaller than the other one. So I think at the end of the day, and again, you're probably afraid to stop me now. Don't be afraid to stop me. But I think this is the picture. I think the additional colors hopefully helped, maybe. And this is, again, I know I haven't done a single calculation yet, which I'm sure is frustrating some of you, and I don't mean to frustrate you. But none of this was a calculation. This was to picture what is going on. And, when it comes to fields, that is pretty important because this field is a pretty abstract idea. It's really, but it's about, the field idea is not just about math. It's about space, and it's about how information is existing in space. It's hard enough to talk about if we don't try somehow to picture it in space. So right now, what I'm asking you to picture is that that point in space at the origin has two field vector contributions emanating from it. A big green arrow going down left and a small green arrow going up right. Those are the two contributions from Q1 and Q2. If there were other Qs, there'd be other green arrows, but this is already a nightmare, right? So now I say on the next, so hopefully that addressed some of the original direct chat questions. I'll keep going. So is this diagram what I just drew? Let me just see. Yeah, so now I do this thing that might throw you off even more, but this diagram now is okay, here, this will help. I'm going to change those to green. Hold on a second. This diagram now is literally transposing, or I don't know what to translate. I'm taking the green arrow from this thing and moving it to the page, right? So this is like green arrow number 1, E1. And then I'm taking that other green arrow, the small one, but now I'm deliberately shifting its tail to the tip of the first green arrow because that's how you add vectors. Like that's how you picture the addition of vectors. Like if all this were literally drawn to scale, which it is not, but if it were all drawn to scale, if I did this now, then I could literally measure out these lines. If I drew them to scale, I can measure them out. And then the final line that completes this triangle, the size of it would be the answer that I'm looking for, the magnitude of the final E vector, and the direction of it, the angle that it makes with some imaginary horizontal. The angle that it makes with an imaginary horizontal, that would be its direction. Now that's what I'm gonna compute that finally. I'm gonna get those things. But this E, final E, is what I'm looking for. And this rough sketch, what's the purpose of this rough sketch? Which I might or might not like want you to do on a final exam. It's to give me a sense of prediction. Like if my sketches are good, I believe my final E vector should point down and to the left or southwest, if you want to call it that. Let's even give direction so we can make this, like if you want to call this north and this south, which you don't have to, but if that makes it easier to talk about, and this east and this west, then it looks from my sketch like my final vector is going to point southwest. So when I get to the end, if my vector is not pointing southwest, it either means I've done something wrong or my original diagram was wrong, but it means something is not aligned in my understanding. But if my final vector is pointing southwest, that doesn't prove that I'm exactly right, but it will. If I were taking an exam and my final answer were pointing southwest, I'd be like, all right, it seems like what I'm doing is self-consistent. It seems like I've got a package of understanding here. So let's see. Now I'm finally going to get to what somebody wrote in the chat. Somebody, I don't remember if it was private or public, so I won't say.
I have a question.
Oh,
I mean, you can answer the chat.
okay. Oh no. Oh, okay. No, well, I'll just say I'm about to start doing the calculation. Someone in the chat said something about calculations, so I promise I'm now going to do calculations. But yeah, you go.
I know this sounds like a silly question, but we have E1 going from P. Like what is that now? So what is that? Southwest?
Right.
Yeah. And we have E2 going northeast, kinda. Well,
Yeah.
but I don't get how the head of the arrow for E1 is all the way down here, and the tail for E2 is all the way up there. But in your diagram, the head and the tail for both kind of, yeah.
Right. Right. No, that's right. It's two different diagrams. You're right. So this, and right. So this first diagram is what I believe is actually happening in space. At that point in space, there's like in a way, let me put it this way. Actually, I think I can exactly put it this way. In a way, this first diagram is like a free body diagram. It's showing all the forces, or in this case, field contributions occurring or acting on a given point. So it's deliberately making that point, that location in space, it's deliberately treating that as the tail of all vectors, because it's just trying to emphasize, like, if you were a proton at that point, you would be pulled southwest like very hard, while simultaneously you're pulled or put whatever, you're yanked northeast not so hard. Like, that's a picture that's just trying to say this is what's happening. It's a picture that based on the facts that we were given. But then this next thing is a step toward actual computation. This thing says, okay, if those are the two forces happening, or the two field contributions exerted on one location, then the net effect of both of them is that they be added together. And the thing about vectors, and I might go off the deep end in a second when I say this, but the thing about vectors is, like, if you go to the simplest case of vectors, if we believe that if you walk like this and then you walk like this, that's equivalent to having in total walked like that, right? Like the whole idea of vectors is they allow us to literally perform addition. Like, vectors are a tool that predate a calculator. If we draw vectors precisely, our whole idea of vectors is that when you place them tip to tail and you literally keep the arrowheads strict, if you place them tip to tail, then a vector that completes a triangle is literally the sum of those two vectors. Like the sum meaning if you walked 3 blocks to the west, to the east, and then you walked 4 blocks to the north, the vector sum of that is that you will have gone 5 blocks, 5 meters. Let's say it's all meters. You walk 3 meters to the right, 4 meters to the north. Then what we're saying is the vector sum of those two things, the displacement that you performed at the end of the day, your final position, as the crow flies, the literal difference between your final position and your initial position is not 3 + 4 = 7. It's 3 tip to tail plus 4. It's 3 side of a triangle plus 4 side of a triangle equals 5 side of a triangle. Like this, and I'm not trying to, I'm saying that this is the deep thing about vectors, is that when you place them tip to tail, you actually perform addition, so much so that if you can measure out the vectors once you put them tip to tail, you get your answer without even having a calculator. I'm going to say that, so I'm doing that in this next page. I'm taking the vectors are acting the way they're acting. They're in space like that. But if I place them tip to tail, then I can start picturing what their resultant is. Let me say, I'm glad you're asking. I'm going to, well, wait, does that make sense so far? Or does that sort of address what you're?
Yeah, it does. Thanks.
Okay, all right. All right, I'm going to take a risk here because this question is a good one. And again, this is one of those, look, and also sidebar to everybody, sidebar on the sidebar on the sidebar. I'm guessing if you guys are all like students often are, like, I don't know, I'm not in the lab with you anymore. I regret that. I don't see you in the lab, so I don't know. It's possible that some of you hate board meetings. I'm just saying, it's possible that some of you hate board meetings. You wouldn't be alone. You would not be the first. I recognize that often people hate board meetings, especially people hate board meetings when they're done correctly, which I'm assuming yours are. I mean, I'm not there to see, but because in board meetings, we sit around a lot and we go backwards in board meetings. They're very frustrating to some people a lot of the time. And I'm not saying they should be. I'm not saying if you're not, like, I'm not telling you to not like them. Ultimately, I love them. But the thing about a board meeting is exactly what's happening right now. The very reason that I'm getting excited is the very reason that some of you might be frustrated, because to some of you, it might feel that we're going backwards. I just want to make this clear. Some of you might feel that some people in the class are asking questions about things that, like, we already said, or somehow we're already in the background before we got here, and you want to move forward to the next example. And I'm very sympathetic to that. I just want to shout out and say, I understand those of you who want to move on. I will. I get it. It's a balancing act. But let me really tell you honestly that actually, the more honestly as we think we're moving forward, the more we can honestly recognize what we didn't get that was back there, the more really we are progressing. The whole thing about board meetings is they force you to go backwards. They're not about covering material. They're about uncovering misconceptions in the material and discovering what we need to straighten out to really move forward. The truth of the matter is, in physics, and I mean this as an encouragement to all of you too, and I mean, take it for what it's worth. The truth of the matter is, I just sort of began to understand undergraduate physics when I went to graduate school. And I just sort of began to maybe see what the heck they were talking about in graduate school when I was forced to teach it, et cetera, et cetera, et cetera. Nobody actually gets physics the first time. I shouldn't say nobody. I mean, some people do, but not me, and not a lot of you, and not a lot of physics geniuses either. What makes them geniuses is that they are willing to keep going over it and over it and over it. And when they get to step 3, they suddenly realize, oh, that's what was going on in step 1. Holy mother of pearl. Like, honestly, we keep pressing forward in physics in the hope that by pressing forward, the stuff behind us will start unraveling itself for you, all of you. That's why I'm always saying you should not be ashamed if you, because I'm going to say right now something about vector. Okay, I'll get back to the point and then I'll get back to the point. But something about vectors that might help maybe one person in the room right now that's sort of based off Christopher's question. We always say vectors tip to tail, tip to tail. Like, I know you've been doing it for, but if you're like me, or maybe Christopher, I was like, all right, tip to tail, whatever. But like, here's what I didn't see. The whole thing about vectors. A vector is an arrow that has that contains and conveys two pieces of information, size and direction. Right now, everybody knows that. I mean, I think all of you know that. The arrow, like how it's oriented, how its tip and tail are, convey the direction. And that's why we make a big stink about the tips and the tails, even though they always seem stupid to everybody, and everybody always just draws triangles and goes back to geometry and just draw. But no. The tips and the tails are the key point. They indicate direction, and then the size of the arrow indicates magnitude. But now here, check this out. If you've never thought this through, the power of a vector, the true breakthrough, the amazingness of a vector, why it's not just a sketch. A vector is literally a computational tool in the same way that a freaking electronic calculator is, or an abacus is. A vector is a computational tool because it contains only those two pieces of information, magnitude and direction. One thing that it does not contain, one thing that's not part of the vector is position. What I mean by that is, it doesn't matter where on the page you draw the vector. It's still the same vector, right? You draw it over here or you draw it over there. As long as it's oriented in a certain way, and as long as it's a certain length, it is that vector. So the amazing thing, and again, I'm telling you this because when it finally hit me, like when I was like 40, it sort of helped me a lot. And it is that the whole thing about vectors is because it doesn't matter where you draw them on the page, because that's not part of the information that they are representing. Since it doesn't matter where you draw them on the page, that means we can use where they are on the page. We can manipulate that in order to get the vectors to do something. So sometimes we draw them this way, like this. So back to Chris's question. We draw it this way because we think this is what the vectors are actually doing in space, so to speak. But then we say, all right, now each of those vectors, its only meaning is in how long it is and how it's oriented. So I can move them around. And if I move them around, I don't change their meaning. Their position is not part of their representation. So I shift the vectors on the page and I put them tip to tail, because now if I believe that all vectors work like displacement vectors, if I believe they all work like walking works, then I could say, well, if I've got a vector that went like this, and a vector that goes like this, if I put them tip to tail, then their net result is a vector that points from the original tail to the bottom, to the final tip. And the very fact that I know Chris, and I'm not trying to use him as an example, but I am, the very fact that I just know that he understood this with displacements and that he got it right and all that stuff, right? The fact that he's asking now, like, wait, what just happened? Like, why do those two diagrams look so totally different? The reason he's asking now is because now we're in a land where the vectors represent something so abstract. They represent fields, which we're just getting used to. So it's really hard to picture like what the heck I'm doing when I move these vectors around. This is the whole thing. Of course, so by doing field vectors, in part, all we're doing is finally seeing the power of vectors in a way, right? And of course, it's harder. So you have to trust, like the whole thing of vectors in the first place was a tool that was built around displacements. And if you trust displacements, trust that from then on in, the way we can picture really abstract things like fields is think of them like displacements in this respect. Again, okay, I don't know if that helped anybody or not, but I'm just saying all these questions are much more legitimate than you guys might think. And anytime it looks like we're going backwards to vectors or something, we are not. We are actually honestly, authentically progressing. But I also know we want to get the problem done, so I will go on. So, okay. Sorry. Also, I'm screaming a lot. And meanwhile, there's a dog. My dog thinks I'm yelling at it, and so it's like either stop or teach me vectors. But okay, okay. So now here's what I'm going to do. Okay, so the summary of everything I just said was when we place, well, sorry, so I'll to read that. It says to add vectors graphically, we place them tip to tail. Again, this was basically lab 3 in physics 203 if you took it at John Jay. But if to scale, we could just now measure, right? And just to, again, remind you, like this picture that I just drew that, seemed surprising, that the point of that picture is if it were literally to scale, you could literally measure. If you can measure that final vector, and that would like literally be the answer. Like that's how powerful these vectors are. So the closer it is to scale, or a better artist you are, the more you have a pretty good sense going in of what kind of answer you're looking for. But now we do want, but I'm not a good art, I didn't draw it to scale. And now we do want the analytical, like we want a precise numerical answer. So we're going to do it. We're going to add analytically to add, like you also did in physics 203, to add analytically. Add components. We're going to add the components, and I'm going to remind you that when we add components, we are just embracing the premise that is running throughout physics. We're embracing the idea that a 2D problem or experiment or phenomenon or whatever is just two 1D problems occurring simultaneously, yet independently. Right? We've said this before. This is a big theme in physics. Hello. It's also a big theme that I can never write anything at the bottom. That we're saying every two-dimensional situation, or three-dimensional, or four-dimensional, whatever, every multi-dimensional situation is really, every two-dimensional situation is really two one-dimensional situations that are occurring at the same time, but totally independently of each other. Huge insight. I mean, this is just another version of Galileo's principle of relativity. We're going to be interrupted again in a second. My wife and my son are going to walk in because I teach in the basement where they walk. So it's going to be another rude interruption. I apologize in advance. We'll try to keep it quick, but I didn't see him all day, so this is what happens. It's not my wife that's rude, obviously. Anyway, so the whole premise of vectors is that anything that's happened, I mean, it's the whole Galileo idea that the laws of physics are the same in all inertial reference frames, in all coordinate systems. And a coordinate axis is the simplest possible coordinate system there is. In other words, whatever's happening in the x-axis is happening and is obeying the laws of physics. And whatever's happening in the y-axis is happening and obeying the laws of physics. And the two worlds are just, and so if you happen to have something happening two-dimensionally, you just have this world occurring at the same time as this world, but they don't affect each other, right? So the whole idea of vectors, the reason we do all this with the triangles and the arrows, is we're going to break each vector up into its x and y components, and then separately, independently, add the x and y components, which is something someone had said in the chat like a million years ago. So here we go. So now, I know some people, I should probably give a minute for people to come back, because for some people, this is all they wanted to see this entire time. I understand that. But yes, I'm about to start doing the math now for those of you who want the math. And the math is not a joke. I mean, this is all math. The computation is not a joke. So here's what we're going to do. Okay, here's what we're going to do. I'm not going to stick with the color green because it's too hard to read, but okay, our procedure.
You can't see.
Oh my God, thank you.
Felix now eats chicken.
Oh my God. Okay, thank you. That's hilarious.
A little bit of that.
I'll tell the dentist. Okay, thank you. Okay. Okay, so this is our procedure, right? This is what we're going to do. We're going to literally, I don't remember if Hammond did, I'm going to literally end up making an XY chart. If any of you are familiar with XY charts from vectors, if that's the way Hammond did it. But okay, so here's what I mean. Oh. Okay. Everything I'm about to do. So, by the way, all that talk about vectors and everything is really all about direction. Now we're getting into the magnitude stuff, the actual computation, the numbers, right? So I'm literally now going to focus fully on magnitudes. I'm going to, in a way, bracket in my mind, like the issue of, I mean, I'm going to be careful, but I'm going to, I'm looking at magnitudes here. So, I'm going to start with that statement. Now, as long as we can get on the same page with this statement, then everything is going to be based on this. But I'm saying the x component of the first vector, of the first field vector, in other words, right. If this is the first field vector, E1, right? Then what I mean is this is what I'm talking about, right? The first field vector is that green arrow that was long, that was pointing essentially southwest at some angle that we don't yet know. I want to get the x component of the field vector and the y component. So the x component of the field vector is the hypotenuse times the cosine of the angle, right? SOHCAHTOA, right? Like this is just, and I could stop on this if anybody wants to ask me in the chat, but this is like good old days of physics 203. This is like, if you have vector A, the horizontal, and it's at angle theta, the horizontal component of it is A cosine theta, and the vertical and the other component is A sine theta. I mean, this is SOHCAHTOA. Right? Specifically, this is that like specifically, I'm saying like that the adjacent equals sorry. Well, yeah, I'm saying adjacent equals hypotenuse times the cosine of the angle, and the opposite equals the hypotenuse times the sine of the angle. That's all I'm saying. So, okay. So let me try to plug in numbers. I'm just going to rewrite this on the next. E1x equals. Well, 1/4 epsilon naught is approximately, let's say 9 times 10. Well, I'm going to round. I'm going to do the 1 times 10 to the 10th thing. Maybe that bothers you, but let's keep it simple. Q, capital Q, this is Q1. Oh, I should say Q1. I'm sorry. That's Q1, which I've lost, I believe was +5. Maybe someone could save me time. I think it's +5. Yeah, +5. Okay. Okay, now we have to be careful. And you're going to want to maybe pay a little attention to how I do this part. And if it works for you, great. And if it doesn't, stop me, because I'm going to do all the rest of the things the same way. Okay, what's r squared. Okay, well, r squared is presumably, that's r, right? Like, that's the original vector, the distance from Q1 to the point. So that's x squared. Let me cut straight to the chase. That is 5 squared plus 4 squared, right? Let me be clear. R, in other words, equals the square root of 5 squared plus 4 squared. Because I'm looking at the original coordinates of, I don't know how to explain that more, but the original coordinates of Q1 it's at 5, 4. So it's, if I make a right triangle, I guess what I'm saying is this is 5 and this is 4, according to the coordinates that were given in the problem. So r is the square root of 5 squared plus 4 squared. So r squared is 5 squared plus 4 squared. Now check this out. What's cosine of theta? Well, you could do a whole bunch of geometry to figure out theta and then take the cosine of it. But we know cosine of theta necessarily equals adjacent over hypotenuse, right? The adjacent here, the horizontal, is 5, and the hypotenuse is 5 squared plus 4 squared square rooted, right? I think I should pause here. Like, I'm saying I just filled in the number. Oh, there's something in the chat. That's almost a relief because there's no way that's obvious to everybody. Hold on. Oh, yes. 5. Oh, cool. Okay. Oh, that's a yes. All right, cool. That was from 2 minutes ago, so I think it's on this, but okay, cool. So what hopefully that's right. So I'll go, so what I'm really saying is, what we have here is E1x equals 5 times 10 to the 10th over, in effect, well, really, sorry. $25 times 10 to the 10th over 5 squared plus 4 squared to the 3/2 power. Yes. Now you don't have to write it that way, but this pattern is going to come up every single time, and it comes up all the time, like on the web, and like it's sort of just worth noticing. Like I don't know how to say anything, but that hypotenuse is getting cubed in effect. It's getting squared because of r squared in the denominator, and then it's getting another power because of how cosine works. So okay. I'm going to pause for a second. I'm also looking at the time. Okay, we haven't. Oh, wait. Oh, sorry. Oh, did I drop an? Oh, thank you, direct chat person. Wait, hold on. I did drop an exponent. You're absolutely right. You're absolutely right. I'm sorry. Yes, I'm very good, direct chat. But please. Oh, where's the coast? Great question. Hold on. So first of all, someone's corrected me in the direct chat, which I do appreciate, and they should. they should. I was literally about to say they should or hould instead of she or he. That's a weird. All right. Anyway, they should submit for points for that. Thank you for the correction. Let me just correct that all the way through. And then there's another question in direct chat, which is a good question. Hold on. No, it should be 8. Yes. Now, there's another question in the direct chat, which I want to answer, but I also want to pause for a second to make clear one thing. This is not an answer to the question yet. This is a crucial piece of information that we need to get the answer. I want to say a couple of things about that. Number one, I mean, are there other ways to add vectors? Yes. But to be really blunt, like, since this usually is on the final exam, and again, your final exam will be shorter than your other exam, you have a lot of choices, but this is usually one of the choices. I mean, sometimes in the past it's been a mandatory problem, whatever. I would highly recommend that you know my way. It's much higher probability of working than some other ways that sometimes work and sometimes don't. So assuming for the minute that part of your job is to learn my way, even if you think you already know another way, then in my way, we are adding by components. This is one of the 4 components that we're going to need to add together. Now, even if you get the components slightly differently or whatever, one thing is I want to pause and say, this is the first of 4 components that we're going to need to put together. Of course, they get easier to get as we go, once we see the approach. But if you did this homework already, if you think you were vaguely on, like some people might have been lost, but if you basically feel like you knew what you were doing sort of, and even if you didn't do it exactly my way, it sort of did involve X and Y components and stuff, I would like you to pause and see if your answer for the X component of the first field contribution is your number vaguely similar to mine. That will be a little different because I rounded. I absolutely rounded. Your number won't be exactly the same, but let's check if your number is vaguely in the 8th order of magnitude or something like that. Because if it's wildly different, then one of us made a mistake, and we should pause on that for a second. So maybe look for a second. If you got answers, if you know in your heart that you did it in a way that is not this at all, like that you were just doing stuff, but now you see it wasn't right, then fine. Like, I don't need to hear about it, and you can still resubmit your homework. But if you feel like you basically were doing something, and I might ask you all in the chat in a second, how many people did something sort of like this, then please check to see if you like my first component. But while you're checking, someone else asked in the chat, what happened to the cosine? Great question. Great question. Because, yeah, the cosine is crucial. The cosine was right there. But what happened to the the cosine is important. Cosine of the angle. So I do mean the cosine of this angle right here, right? But the cosine, but because of SOHCAHTOA, the cosine of the angle is equal to the adjacent times the hypotenuse. Wait, let me back up for a second. I see something that's confusing. The cosine of the angle means is there because we're just looking at the horizontal. No, first let me answer the question. The question is what happened to the cosine? Cosine means adjacent over the hypotenuse. So the adjacent, if you look back to your original R vector, the original R vector in this picture, if you look at the R1 vector, the blue line, the blue arrow that was originally written there, it started at the point 5, 4, and it went down to the origin. So that's like the hypotenuse of its own little mini triangle where I could drop, height and altitude, and I could make a base, and I could say, and I'll erase that in a second because it's getting crowded, but like that original R vector is making an angle with the horizontal that is known to us because the coordinates of this point are 5, 4. So the base is 5 units wide and the height is 4 units long. And therefore the hypotenuse is square root of 5 squared plus 4 squared. So what we said is the cosine that we're looking for right here, the cosine is the adjacent over the hypotenuse. The adjacent is 5. And the hypotenuse of that r that I just looked at, the hypotenuse is this right here, square root, because it's Pythagorean theorem. It's the square root of 5 squared plus 4 squared. So the cosine of the angle, like, so we never put in an angle. You're absolutely right, direct chat person. Like, in order to get cosine of the angle, we didn't solve for the angle and then take cosine. We just skipped straight to, oh, cosine of the angle must be the x piece divided by the hypotenuse piece. So it's 5 divided by 5 squared plus 4 squared, square rooted. And if this helps at all, I don't know. But in the next step, when we get the vertical component, we're going to do sine instead of cosine. Well, what we're going to do there is put 4 instead of 5 over 5 squared plus 4 squared, square rooted. That's such a good question that, did I answer? Could you maybe tell me, direct chat person, whether I, okay, cool. Thanks. You're so polite. I appreciate it. I'm not laughing. I am. No, I appreciate it because I know I'm like forcing you to be, but okay. To everybody, there's a subtlety. The really reason that's a great question, well, first of all, because you could not possibly ask that question unless you were like trying to follow this and pay attention, right? But also there's a subtlety in that question too. Even those of you who think like, yeah, I saw that. Yeah, adjacent over hypotenuse. Like, let's keep going. Come on. Well, like, notice one of the reasons that she or he had every right to ask that question is that actually the theta that I just used, like the subtlety of this is, we're trying to find the field contribution. Let me put it this way. The horizontal component of the field, the thing that we just figured out to be 9.52 times 10 to the 8 Newton per Coulomb, that's the horizontal component of the field. What that is the field, like in other words, 1 over 4 pi epsilon naught q over r squared. It's all of those numbers together times cosine of theta. What it isn't, let me put it more specifically. We plugged in the whole r and squared it, put it into the denominator, right? We put in the whole r, the diagonal line. We put in square root of 5 squared plus 4 squared. We plugged that in as r, squared it, did all this other stuff, and then multiplied all that by cosine to get the x component of the whole mishpucha. Rather than what we didn't do, the thing I used to do when I was wrong, what we didn't do was just plug in 5 for the r. Please notice, in effect, what I'm saying, we did the cosine component of the blah, 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 r squared. We did the x component of the blah, 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 r squared. We didn't just plug in x for r. We did the x component of the field contribution. I don't, like, we had to use all the numbers to get the field contribution. And then we just multiplied by cosine just to get the, in other words, we're getting the horizontal leg of the field vector. We weren't getting or just plugging in the horizontal leg of the r. We used the r to build the field and then took the x component of it. The final point I'm trying to make with that, and why it was such a good question, is in order to do cosine theta, I did just use 4 and 5. Even though I didn't know what the vertical and horizontal components of the field were yet, I just plugged in like 4 and 5 as the opposite and the adjacent. I just used the numbers from my original r because whatever the theta is of the original r has to be the same theta as the final field vector, right? Here's the thing. All of this is based on r. We drew r first and then shrunk it and then stretched it to make e. E is a totally different vector from r, but it's totally built from r. It has a completely different magnitude, but it absolutely has the same or the exact opposite direction. So whatever I know about the angle of r, I absolutely use for the angle of e. That's why I was able to just to answer her or his question, why I was able to say cosine was like 5 over square root of 5 squared plus 4 squared. I just pulled those numbers from the r because I know that the theta for r has to be the same as the theta for e because one vector was built from the other. That's what's That's how important R is for what it's worth. But okay. I'm gonna keep going. So that's did anybody it's 6 o'clock. Wow. Okay. I'm gonna keep going to the next component. But if anybody, is there anybody, did anybody get any do I want to do this? I don't want to put anyone on the spot. How about I ask this? I'm gonna change the, could you, I just want to know where we're at. Could everybody in the direct chat, in the private chat, just put something like either I tried, but I gave up, or I didn't try this yet, or I tried a different way. Now I see that it was wrong, or I did something like this and got a similar answer, or I did something like this. I think it's like this, but I'm getting a different answer. Could everybody just in the direct chat just tell me something? And there's no shame again. Even if you write, I never tried it. I don't care right now. I'm just trying to figure out who I'm like what. Oh, okay. Wait. And honestly, I see people are doing it. Okay. Oh, okay, cool. Okay, great. And part of why I'm asking too is I want to make sure if anybody did the exact same thing I did, but got a totally different answer, I don't want to move on if that's it. Okay, oh, okay. Oh, great. Okay, this is very honest. I appreciate it all. Okay, fair enough. I'm looking at, and I'm not going to respond to anybody, and I'm just looking. Cool. Oh, okay, cool. Okay. Oh, okay, cool. Oh, cool. All right. Okay. Okay. Oh, this is very honest. All right, I'm learning a lot from all this. And everything you guys are saying in the chat, if nothing else, it makes me feel like this is worth it. I mean, you feel like we're not totally wasting your cool. No, and there's all kinds of answers in the chat, but it does seem to confirm for the people that actually, and enough people did different things and other things that I don't feel like I'm wasting your time. But the people that did do something like this do seem to be saying that they got something to the 10 to the 8th. And that if they use the exact number on the sheet, maybe they got like 8.6 times 10 to the 8th instead of 9, which makes total sense, and that's fine. And again, if you were in the exam, I mean, you see what I do it this way because it's like easier for me. It's just easier. And that's, you do whatever, but cool. But the main thing I would look for on the exam and stuff is orders of magnitude. Okay. But I do have to admit, and oh yeah, and if you're sending to Yavra, okay, cool. No, I see. And if you went to the Yavra board but now came back, cool. So I'm going to go on now. And I do appreciate that some of you, and you're all very polite too, but I mean, one person wrote, I do have to read this, I won't say the name, but one person wrote, vectors are kind of my enemy, but it's getting better with this lecture. I mean, I hear you. I totally hear. And please, I hope you all understand that like I'm teaching you from the point of view of like, I chose to do this for a living, right? I chose to be a physics major in undergrad. I chose to go to physics grad school, right? And so like I chose it, right? And not even because I thought I was that good at it, because actually I wasn't. I sort of was, but not really. But I chose it. And I'm just telling you that even as a person who made it their life on purpose, and I've been doing it now for, I mean, I graduated from college in 1992. So I've been thinking about this stuff, like 30 years. And I'm telling you, like, I suffered as much as you, all this stuff. The only difference is that for some reason it was worth it to me to eventually get, and now I get stuff because I've been doing it so many, but none of this stuff, it's always easier than it seems like it should be once you get it, and it's way harder than it seems like it should be until you get it. All of it. Please don't give up, or please don't think it's you. It's not you. Whoever you are. And if you are getting it, by the way, rock and roll, and Quark bless America. And like any of you who's getting any of this right now, you're definitely ahead of wherever I was at the time. For if that means, I mean, not that I'm anything. All right. Anyway, so we're going to go on. But I really think you guys are trying, and you're with me, and it's Zoom too. So it's very inspiring. So we'll go on. I'm going to go to the next component. There was something I'm just going to go on, right? Okay. So I'm going on. So we're going to now, oh, no. One other thing though, it's cool if you, I do appreciate the honesty in the chat. If you, well, no, I don't have it. I'll go on. All right. So the next component. So E1y. Now we can race along a little bit faster now, because it's the same procedure now. E1y is going to be, okay, 1 over 4 pi epsilon naught Q1 over R squared sine of theta, right? So that is, okay, I'm calling it 1 times 10 to the 10th. That's a severe rounding. And Q still Q1, so still 5, I believe, positive 5. And R squared is still 5 squared plus 4 squared, which I think was 41 or something. And now sine of theta, back to the direct, sine of theta will be opposite over over hypotenuse. So that should now be 4 over 5 squared plus 4 squared, but to the 1/2 power, right? Stop me if I've just messed something up, but I think that's all right. So it's now 20 times 10 to the 10th, which I'll change to 2 times 10 to the 11th. And in the bottom, we have, I think it was 41, right? 25 plus 16, yeah. 41 to the 3/2 power. So we have 2 times 10 to the 11th over, and I forget what 41, but it's the same. Is that right? Yeah. 40. So 2.63 times 10 to the 10. And again, this all sort of makes it so that we have some chance of, it's partly so that we can be macho and not have to rely on a calculator to the extent that we can, but it's also so that we can see what's going on. So we want to postpone calculator calculations to the last possible minutes. So for the longest possible time, we have some intuitive check on what we're doing, right? Like even this, I should basically be able to do in my head. I mean, 2 divided by 2.63, it shouldn't be that hard, but apparently it is. Yeah, so this should be, so I think that's this. And someone check me, I better do that more slowly, but I believe that's right for this one, also in newtons per coulomb, right? Oh, and again, each one of these is in newtons per coulomb. Each one of these is a component of a field vector, which means in and of itself, it's a field vector, right? Each one of these is it's how, so that first answer that we got, by the way, that's how much we're being pushed to the east or to the west, I mean, in this case, to the west, by just the first charge, right? That's what that first number meant. It's how hard we're being pushed to the west by Q1. And this one is how hard we're being pushed to the south by Q1. And by we, I mean we, if we are a positive 1 coulomb of test charge. But I'm stalling slightly because I want you to check. Could someone just check? Can you check the math of, even whether you got this answer or not, can you just check the math of literally what I just did? Because I'm insecure of that calculation. Also will keep you, I mean, I'll check too, but. Yeah, actually, all right. Well, if no one's gonna, all right, I believe myself, but you should check it. You should really double check it. But all right, so this is now E1 sub y, sorry, sub y. And these are pure magnitudes that I'm tracking. These are not saying anything about direction. We're gonna have to be careful about that in a minute. But now we're gonna go, okay, 2 more steps. Maybe you could just, if I were really cool, I would just tell you to do this on your own right now, but I'm not really cool. So we're going to go E2x now, right? And that is, I'll cut straight to the chase. It's going to be 1 times 10 to the 10th times, okay, now we're talking about the other charge, Q2, right? So it has a magnitude of charge of 2. Oh, cool. Thank you. Oh, and she went public. Yo. Oh, and 2 people went public. Oh, no, what? 1 person went public and 1 person went, thank you. I totally appreciate it, public and private person. I mean, I totally appreciate it, Valentina and direct person. And I'm not being sarcastic. I always sound sarcastic. It's a problem, but thank you. Okay, cool. And you should submit that for points. And I hope you all see that, even though I still totally owe you exams, I think almost all of the points that you've ever submitted for outside the exams, I think you pretty much have all come back to you, and you can see they're adding up. And hopefully they're making you feel more secure about where you are in the course if you've gotten a lot, whatever. I'll stop talking. And you also got, okay, great. Thank you. Awesome. That's 3 people. Definitely submit those for points. Okay. So now we're on to E2x. So I'm doing the constant times the Q2, which I believe the magnitude is just 2, right? I better check, right? I'm not worried about positives or negatives right now, but I believe the magnitude of the charge of the second charge is 2 coulombs. So I put 2 in there, right? All over R squared. So now R squared, whoops, sorry. So R squared is going to be, well, now we're talking about that second charge. So it's going to be 10 squared plus 3 squared. I hope you see what I'm saying, right? Like the hypotenuse. Notice that's R, the hypotenuse, the original blue vector all the way on the page that I'm not going to flip to right now, right? That's R squared. And then all of this times cosine of theta. I'm cutting to the chase. Cosine of theta 2, I should say, right? This is theta 2 now. So the adjacent will be 10. And the hypotenuse will be 10 squared plus 3 squared square rooted. Please stop me if that, like, please stop me if you want to. So now I can shorten that and say it's like 2 times 10 to the 11th. I'm skipping more steps, and you could do this on your exam too. Like once you get it on, then you can like be more as you go. But so 20 times 10 to the 10th is the same thing as 2 times 10 to the 11th, all over 109, like, right, 109 to the 3/2 power, right? So 2 times 10 to the 11th, all over the floor, 109 to the 3/2 power. And that's a kind of thing that you can just do on you. Like on my calculator, I just do 109 to the power of 1.5, if you see what I mean, right? It's like a fast, okay, you get my point. So 1.13, sorry, 4 times 10 to the 3rd. And strictly speaking, I should make this a 2.00. I don't really care, but I sort of do. And now I can, so that should be, and you know, the goal of all this too is like, if the number in the denominator were easy enough, if it were like 1, like I could literally do this part without a calculator, but I can't exactly. Okay, so I think we get 1.75 times 10 to the 8th. You should check me on that. But you know, I'm just doing 2 divided by 1.14 is 1.75, and I'm just then subtracting the exponents. Because wait, someone said I made a mistake. Wait, I might have made a mistake. Yes, I got, isn't it -2? Isn't it -2? Wait, isn't it -2? Maybe. Where's the -2? Oh, isn't it -2? Hang on. All right. Someone's asking in the direct chat about the negative. I see what they're saying. They're asking, shouldn't I be putting in -2 for the charge? That's a very good question. I am not. I'm now, this again, this is a strategy thing. There are different strategies available to you to do this. My advice, and even if this was a promise from the class, like even if we don't get to other things by the end of this class, we will certainly get to the end of this. And you will see at the end, my strategy here is I'm continually in my mind trying to separate the issue of magnitude from the issue of direction. That's like a big sort of emphasis of all of this, because I'm kind of saying direction is now sort of important and complicated enough when you talk about fields that it's hard enough on its own. So let's deal with direction separately with all the R hat vectors and all that, and deal with magnitude separately. So what I'm saying, I mean, it's a great question. What I'm saying is I am literally just trucking out the magnitudes right now. Yes, I am deliberately ignoring that negative sign in the charge, because what that negative sign has to do with ultimately is whether the vector is a pull or a push in what direction. I am going to incorporate that. You will see there will be a very important big step when I take the pulls and pushes and the directions into account. But I'm going to do that when I'm explicitly thinking about direction. For me, it is easiest to keep these ideas separate. There's other ways you could do it. As long as you're self-consistent and you're sure you know what you're doing, this is not the only way. But I'm very glad that, and anybody who's listening now, like, please note, this is exactly the kind of thing that you would maybe notice when you were studying by yourself. Like, you would maybe really suddenly see that too and think, wait, did Yaverbaum, is this a typo? Because Yaverbaum does make mistakes. Like, and it could have been, but it's not. It's not a typo. I'm deliberately leaving out the negative right now because I'm only trying to compute magnitudes. And once I get these 4 magnitudes, these 4 pieces, the way I'm going to put them together will incorporate the direction. But I'm very glad that somebody asked that. And I hope it's clear. Okay, cool. I love that person totally always makes it clear to me that that person is totally in this class. Okay. Okay, so, and I think, did someone else check the math? Yeah, so did anybody check the math? But I think this, oh, and you got the same answer. Okay, great. Thank you, same person, awesome, thank you. So we now have that E2x approximately equals 1.75 times 10 to the 8. And really, okay, so technically well, notice there's no vector symbols over the E. I'm literally just writing E2x, meaning just like the size of the x component of the E2 vector. Okay, but this is all in newtons per coulomb. So this now says that second charge is either pushing or pulling is to the east or to the west this amount, 1.75 times 10 to the 8 newtons per coulomb. So finally, I have one last component to do, E2y, and it will be 1 times 10 to the 10th times the 2 again, all over the what is it, 109? 109, okay, all over the 109 times now the sine, and the sine is, I think, 3 over the 109. Is that right? Yes. 109 square rooted. Okay, so we get, and hopefully you also see that this is very hard at first. Like the very first one we did is like, you had a lot of questions, but hopefully once you get it, then it's like repetitive a little bit, maybe. So we get 6 times 10 to the 10th on the top, and we get 109 to the 3/2 on the bottom, but we already know what that is from before, but I totally forget it. 1.14 times 10 to the 3rd, okay. Right, okay, so hopefully this, and so hopefully, so then I just do like 6, so I mean this like almost 6.1, I mean 6 divided by 1.1. All right, so approximately 5.26 times 10 to the 7th. You see what I'm doing, right? I'm just dividing the coefficients and then subtracting the exponents, because like that's badass or something. Okay. And maybe someone could check me on the mathing, but I think that's right. Oh, and notice one little subtle thing. If you, oh, did you got the same? Oh, that's okay. Notice one thing that is happening. I'm just flipping back because just notice one thing. Our first x component was like 9 times 10 to the 8th. Then our next x component was like 7.6 times 10 to the 8th. Then our where'd it go? Our first, wait, what? Oh, yeah, then our second x component was like 1.7 times 10 to the 8th. I'm trying to say that's smaller than the other one, right? And the y component was like 5.26 times 10 to the 7th. Like our second, in other words, the two components of our E2 are both smaller, I believe, than our two components of the E1, as we predicted. Oh, and you got the same answer. Great. Thank you, Direct Chopper. You are rocking today. Many of you are, but you know who you are. You are, wow. Awesome. I hope you submit all of it. And again, all of you, if you do multiple things like this, you can submit them multiple times. Like just collect points. Like they're there for the taking. I want to give them to you. I am not Tom Nook. I will not overcharge you. As for second mortgage on your house. Okay, so I think as we predicted, the second field vector contributions are smaller than the first because the R2 is bigger than R1 and Q2 is smaller in magnitude than Q1, right? So again, and also again, just note, like when you looked at the blue arrows on the first picture, the blue arrow, the R vector from Q2 was a lot bigger than the R1 vector from Q1, but the field vectors were the reverse, like they're not the same vectors. One's built from the other. Okay, so now what the heck do we do? I mean, I think you see where this is going, but now this is what I do. We now have two X components. We have two Y components. The whole idea of the isotropy of space or the homogeneity of space is that there's this X world going on while simultaneously, but independently, there's a Y world going on. X doesn't affect Y and vice versa. So I'm going to literally, what I do is I make a chart. I literally go like this. Hello. Yeah, I go like this. I'm going to literally add up. I'm going to add up, the X components from the two, and I'm going to add up the Y components of the two. I'm just going to add, right? I'm going to add, but here's the catch. When I add, I'm going to add because we're adding. I mean, like, no joke, like we're putting together two vectors. So I'm going to add the X components no matter what. And I'm going to add the Y components no matter what. But now I'm going to address the direct chat person who was asking, hold on, what happened to the -2? Like, here's where I'm going to take that into account. And here's where all of my labors over arrows and tips and tails really come in, and all my diagrams really mean something now. Because now I'm going to look back on any one of my diagrams, but let's say specifically, I'm going to yeah, maybe I'll even redraw it for, okay, I'll try to remember. Okay, remember this diagram that Chris was asking about, the green diagram on the top, right? It says that E1 is pointing southwest, right? Whether you call it a push or a pull, I mean, it was a push, right? It was a push, but what did that mean? It meant it was pushing the thing to the west and to the south. Like southwest means west plus south. And E2 was pulling the test charge northeast, right? So maybe I'm going to redraw those. Right, so recall. And I believe E1 was like this. And E2 was like something, I'm not going to get it exactly right, but E2 was something like this. Right, so this is E1X, and this is E1Y, and this is E2X, and this is E2Y, right? So now I'm going to take that into that, my arrows and my understanding of the physical nature of the problem, I'm now going to take into account. I'm going to say, okay, the EX1 component, the number was whatever it is. The number was like 9.52 times 10 to the 8. Please help me remember that. 9.52 times 10 to the 8. So I'm going to put that in my chart, but I'm going to say it's 9.52 times 10 to the 8 to the left, to the west, right? So that should get a negative sign. Negative 9.52 times 10 to the 8, right? I'm putting the, I hope you see what I'm doing. Now, again, are there other ways to do this? Yes. But whatever way you do, you have to be very careful about, because the whole key here is it's very easy to forget about negatives and positives, but it's equally easy to double count them by accident. Like a lot of people, like, for example, even if you think you understand why I just put this negative sign in, I will tell you right now, if you put these negative signs in appropriately, like I'm about to, but you also put the negatives in the chart, like in the answers, like you would double count. So you have to be very careful about when you count direction. Don't count it twice, but do count it. So the E1X is going to the left, so it gets a negative. The E1Y, of course, I've already forgotten the number. The E1Y, I just passed. The E1Y is 7.60. Okay, times 10 to the 8. 7, but that's going south. So that's also a negative. And of course, I just forgot what the number is. It 7.68? Because sometimes I just forgot. I knew I'd do that. I think it's
Hey, child.
hey, buddy. How's it? I can't wait to hear about it. I'm almost done.
As
As soon as I'm done, right? It's
How long?
20 minutes, which is very short, but I got to do this.
What are you gonna do?
I got to continue teaching. They're all there. You just can't see it. Okay. Good to see you. I can't wait to hear how it went.
Bye, Dad.
Bye. Love you. Love
By
you.
the way, I tried it on time.
Oh, wow. That's awesome. E1Y 7.60. Is that what I said? 7.60. 7.60. Okay. Okay. So the key point, so I'm just putting those numbers in the chart, but I'm deliberately putting negative signs where they apply. And please notice too, like this negative sign at the end of the day is because I think the vector is going west and or south. I've already taken into account all the, whether it's a push, whether it's a pull, whether it's positive, negative, like all of that fed into each one of my diagrams, so that at the end of the day, I trust my vectors and I say, fine, the X and Y contributions of the first, due to the first source charge, they're both negative contributions, i.e. to the west and to the south. Then the E2 contributions, looking at my picture, they're both going to be positive because it's a north pointing and an east pointing. So it's 1.75 times 10 to the 8th, positive. And finally, a really, really small contribution that's barely going to make any difference, 5.26. Right? So now this is my chart, and we are almost done, Although, well, anyway. So this is my chart. So now it says to literally add. I'm going to add, but some of the numbers that I'm adding are negative numbers, but I'm adding them, right? I don't want to double psych myself, which people do all the time. But so I'm going to add. And I'll get negative 7.77 times 10 to the 8th. First, I'll turn it to Marge Simpson. Hold on a second. Okay. Negative 7.77 times 10 to the 8th. And then over here, well, this is barely, like, you've got to be, it's two different exponents. So it's barely going to make a difference. It's, you know, the second number is barely going to change the first number, but right. We get like negative 7.07 times 10 to the 8th. I hope you see what, right? Because it's like saying 100 million minus 10 million. Like, so you get like 90 million. If that, I don't know if that makes, but right, like the second number is like a tenth as large as the first number. So it doesn't really change. You get what I'm saying? All right. So those are our two, or tell me if you don't, but so now we're almost done. And by the way, for anybody who said they're beginning to understand vectors now better, like, great. Again, let me say again, like everything I'm doing now, technically we're just adding vectors, but adding vectors is not a joke. And the whole thing about adding vectors is it's particularly abstract when the vectors themselves represent particularly abstract ideas, right? If you feel like for the first time you're actually seeing what's going on when vectors are being added, then you are not wasting your time. So what's the final step? The final step is we have the total amount of X and we have the total amount of Y in what? In the final field vector that we're composing, right? So what this means to me is I draw one last Pythagorean triangle, right? What I say is, okay, the ultimate field vector that I've been trying to search for this entire time has an X component that points to the left, 7.77 times 10 to the 8th newtons per coulomb, in a Y component that points down, left, west, and that points south at 7.70, whatever, times 10 to the 8th. So I literally draw that. I go, okay, and here's a big trick to the big pro tip for vectors. You might even notice, every one of the triangles I draw, I always draw the horizontal first, and from the tip of the horizontal, then start the tail of the vertical. Always, always. That's a major pro tip. Honestly, that is a life hack right there. I don't even know what that means, but it is. And it's one of those things that you won't appreciate until you actually practice this on your own. Everything I'm saying might sound like it makes sense. Then you practice on your own and you realize that what I'm saying is one out of 50 different possible ways you could do these things, but 47 of them are wrong. And one way to ensure that you're doing this all right, and one way to ensure that you actually measure the appropriate angle at the end, and that everything works out in a non-confusing way, is always draw the horizontal first. So here's my horizontal. It's 7.77 times 10 to the 8th, right? But it's negative, so I drew it going to the west. Oh, and I drew it in the wrong. I just violated my own pro tip. Sorry. I mean, it's correct, but I should have drawn it at the top of the page. So I go, okay. 7.77 times 10 to the 8th. And even here, you notice I don't put the negative sign. The negative sign is being indicated by the fact that the arrow is going to the left. Then from the tip of that arrow, I start the tail of the other arrow, the Y component arrow. That arrow goes down. Its tail starts at the tip of the first one. Always draw the horizontal first. Even if you don't know why I'm saying that, try it the other way. You'll see why in a second. So I draw the other one. Now it's going down. It's not as long as the first one because the other one is, it's approximately on the same scale, but it's 7.07 rather than 7.77. Okay, but it's also 10 to the 8th. Oh, and I also drew a 2. Hold on. Didn't give myself enough room. Sorry. Okay. So it's approximately as long, but here it is 7.07 times 10 to the 8th. And now, well, maybe it's not quite as long. Okay. So now, the answer I'm looking for, the ultimate answer I'm looking for, the field vector is this, right? This is the field vector. The size of that arrow, the size of that hypotenuse will be the magnitude of the field vector. Okay, I'll go like this. And the direction of that field vector will be whatever this angle is right here. Let me tell you that part of the reason I always draw horizontal first and then vertical from the tail of the horizontal is because that will ensure that the angle I'm looking for will be between the two tails, because there's always this thing of like, which angle should I pick and stuff like that, right? Well, if you do this correctly, you'll always end up that the angle between the two tails, which is the angle that actually does represent like what direction something's happening in, will be the angle measured from the horizontal. You'll know you've done something right if the angle between the two tails is, first of all, not a right angle, and second of all, is the angle measured from the horizontal. That's perfect if you've done it like that, because then the point is that, okay, so the magnitude of E will be the square root of 7.7. Let me browse. 7.77 10 to the 8th squared plus 7.07 times 10 to the 8th. Like, this is Pythagorean theorem. I think you get what I'm doing there, right? Okay, so we'll get that. Okay. So basically 1.05 times 10 to the 9th, I think you should check that. So the magnitude of our final answer is approximately 1.05 times 10 to the 9th newtons per coulomb. That's the strength of the field. And the direction of the field will be the arctan, right, of the opposite over the adjacent will be the arctan of 7.07 divided by 7.77. And I don't need to do the point. If you think about it, like the 10, the 8s cancel in that fraction. I don't have to worry about them. It's the same ratio. Sorry. So, and for this problem, I'm going to keep it in degrees so that we can picture it intuitively. This isn't like a wave problem or whatever. And I hope you understand why it's arctan, because tangent of angle equals opposite over adjacent. You could do anything. You could say sine of the angle equals opposite over hypotenuse. But the whole point is I just figured out the hypotenuse. So I sort of trust the opposite and the adjacent slightly more. So my habit is I always use tangent to get the final angle, but you have to do arctangent, right? Like the tangent of the angle is the opposite over the adjacent. Therefore, the angle itself is the arctangent or the inverse tangent, whatever you want to call it. And that is, I believe, yeah, like approximately 42.3 degrees. And now watch this. Because I did all of this correctly, because I set it up so that my final Pythagorean triangle was a horizontal, and then at the tip of the horizontal started the tail of the vertical, so that my angle is up here between the two tails. Then what is that angle? That angle means 42.3 degrees south of west, right? Like that angle. See, I always like my angles to be opening up from the horizontal, because then what the angle showing is, what that angle is if I call it 42 degrees, I'm saying it's 42 degrees south of west. Like I opened it up from the west, it's 42 degrees south of west. If I measure that other angle, which people do a lot, if I measure from the vertical, then what I'm really saying, if I get 42, if I get the other angle and I say that it's 50, I'm losing my mind. If I say that it's 47.7 degrees, the other angle, then that's not, the reason it's confusing, that other angle, is because that's not southwest. If anything, that's west-south, which is totally awkward at best and meaningless at worst. Like, but if you want to say a thing that people in the world will understand, like 42 degrees southwest, what you're really saying is the angle is that far south of west. So you want to make sure that your angle is opening up from the western horizon line. Okay. Anyway, that's our answer. I believe, like, that's our final answer. It took that much work to get that final answer. Now I'm going to pause. I know we only need 8 more minutes, so I won't. I mean, there was something else we were going to do today. We're obviously not going to do it. That's fine. That's a lot. First of all, I'm going to change the view on the screen. I really do think you guys, you participated a lot and you hung in there a lot for a very thick. I mean, we just spent 2.5 hours on one computation. That doesn't mean it would take you 2.5 hours to do it, right? I mean, it means it took 2.5 hours for me to talk us through it. It might mean that the very first time you do it successfully, it might take you 1.5 hours or something, but obviously once you get used to it, it takes, but it is a thick computation to get the field at a point to get the field at a point in space due to 2 point sources of charge. All of that work was to figure out what the field is here as resulting from or created by a point of charge over there and a point of charge over there. It's a lot of work. I mean, even if you know exactly what you're doing and you do it quickly, it's a lot of work. We have 6 minutes. I'm not going to start anything new or anything like that. But first of all, I just wanted to, can you please raise your electronic hand if you feel like you get this problem now? Well, that's fair. Wow. Okay. Cool. Awesome. Well, that's like almost there. Okay. Great. Okay. Thank you. Awesome. Cool. And I know, look, even for me, I'm exhausted and I got to talk the whole time. And if you're having to sit here and listen to it, like it's super exhausting. I know that. And I also know that those of you who did participate, you're helping yourself to stay alive in the class. Oh, that's very honest. That's very honest. Yeah. And by the way, and you should, I mean, and there will be, I will give you another practice on this, but also make, oh my God, oh my God, oh my God. Wait, 5 more minutes. Hold on. It's not 6 minutes. You got to let me finish the 6 minutes though. Wait.
6 minutes. Okay, sorry.
Thank you. Okay, you're being very polite. Appreciate it.
You just say something
Okay,
relaxed.
okay, very good. We're in a.
No one believe him.
Yes, they are.
Your career will be messed up.
Okay,
Just don't.
okay. Thank you. That's very funny. Okay.
Type in the chat FY.
I,
FYI.
that's funny. That's funny. Okay. FY says this. Okay. I don't even want to know what's in the chat now. I know you're getting sick of that. Is that? Oh, cool. Oh, thank you. Someone says, okay. So one person's saying that it seems a lot easier now that they understand it, which I appreciate. But then someone else is also saying need some practice, which I totally appreciate. And yes, and please know, my job, and maybe my passion is to try to talk about these things in a way that ultimately show you that they ultimately can be easy, but I don't want to fool you. Like if I can break this down and make it not even easy, I don't even think it is easy. I think it makes sense. I think it makes more sense than it looks like when you first look at it, right? That's like my goal. But if I even have any ability to break it down and explain it in a way that helps you at all, that is only because I've been forced to practice it so many times. I mean that. None of this meant this to me the first time I saw it. It's only because of practice that I can now see it. So, I mean, first of all, I want to echo the person that's saying needs more practice. And by the way, practice, one thing I learned also was in graduate school or something is like, you don't have to do exercises 1 through 89 odd, if you know what I mean, to practice. You don't have to have a million different exercises to practice. You can literally practice the same one over and over, and it is still practice. It's like practicing the piano. In fact, honestly, physics is a lot more like a musical instrument or a foreign language than it is like a body of material. You could take this exact problem and just keep, and that's how I ultimately learned to study. And that's why we do things the way we do with the practice tests and all that. If you just try this problem over and over and just every time you're stuck, look at what I did, that is practicing. If you want to eventually change the numbers or have your friend change the numbers slightly, sure, go for it. But it's still practice, even if you do this exact one. I promise you that. Also, I want to say that all of this is as much psychological as it is intellectual, really. It really is. It's a lot about confidence and all that kind of stuff. Really? And so also for any of you who then when you see it, when it's over and you're like, oh, now it makes sense. Like there's a tendency for people to then go, oh, what the heck? Like, why didn't I see that before? Oh, it's like totally obvious. Like, and they either then go, oh, I don't need to practice it. It's like obvious now, which is wrong. And I appreciate that Key realizes that, but also a big mistake that people make. They don't see something first at physics and they're like, well, that's absurd. I have no, like, that's outrageous. I can't do that. I don't even know what that is. Then it's explained to them. And then they're like, oh, that's totally obvious. It's self-evident. I must be an idiot that I didn't see that before. So forget it. I'm not cut out for this. Don't think that either. Even if it now seems easy, but it didn't seem easy yesterday, that's because you just sat for 2.5 hours and slogged through it and asked great questions and blah, blah, blah. It's always easy after the fact. That's why I hate that word. It just means it makes sense. Just like if not I, because I'm terrible, but if one of you played a Bach piece on the piano in front of me right now, if you played it well, or you danced ballet in front of me right now, you'd be so graceful, you'd make it seem easy. And I'd be like, oh, I know that piece now. And I would recognize it if I heard it. That doesn't freaking mean that I could play it, right? I mean, and it doesn't mean I should chastise myself if I can't play it the first time. Anyway, you get my point. All right, wait. Now, we do have to go. I know it's 2 minutes. Wait, okay. I will submit more. I mean, I will post more practice questions on this, like in the practice exam over the weekend, I will. But I'll also say, I don't think you should look for many, many more. I think you should first, honestly, try to practice the same one a number of times. I do think that is actually more important than people realize, but we could talk about that in a minute. Yeah, the update, I will send updates on that. Good question in direct chat. I will be posting updates and scores and stuff as we get into the end of this week and the weekend. I don't have any more update right now. I will post a lot of things this weekend. I can assure you that it'll be shorter than this. You have to go we have to go. I was gonna say one of that, but I'll save it. I think you guys have done very well today. Just keep doing what you're doing and you will do great. And the tie will go to the runner. I think we're all probably exhausted. So I'm staying for anybody who has questions or anything like that, but thank you all very much. More will be coming to you, but thank you. Thank you. You've done a great job. Thank you. Awesome. And I'll turn off the recording in a second. Okay. Oh, yes. Have a good week. Thank you. You too.
Have a nice day.
Oh, yes. Thank you. You too. Thank you. Awesome job. Great. Okay. Okay. I'm stopping the record. Great. Wait, Toiba, are you still there? Hold on. Are you still there? You're the only one that, wait, Toiba, are you still there?
Yeah, but I'm gonna leave right now. I'm sorry.
Okay. No, so you're the only one. Oh, I'm stopping the recording.